Hey everyone. Tonight we're embarking on the longest journey into the ocean's darkest corners that we've ever attempted. Over the next several hours, we'll explore the most chilling, mysterious, and utterly captivating secrets that lie beneath the waves. From creatures that defy biological logic to underwater phenomena that scientists still can't explain. From vanished submarines that disappeared into liquid silence to ancient relics that suggest civilizations we never knew existed. The ocean is not just water and salt. It's a keeper of secrets, a graveyard of the unknown, and a living entity that breathes mysteries with every tide. So before we begin this marathon descent into the abyss, go ahead and like this video if you're ready for the ultimate deep dive. Subscribe only if you genuinely want to explore the unexplained with me through these long, dark hours. And drop a comment telling me where you are in the world and what time you're watching this. I love knowing who's brave enough to spend hours in the ocean's embrace. Now settle in, get comfortable, maybe pour yourself a warm drink and prepare for a journey that will take us to places where reality blurs with nightmare. Let's begin. When people talk about space exploration, they often say it's the final frontier, but they're wrong. The ocean is Earth's true final frontier, and it's been waiting right beneath us all along. We've mapped more of Mars than we have of our own ocean floor. Think about that for a second. We can see distant galaxies billions of light years away, but we can't see what's happening 7 miles below the surface of our own planet. The ocean covers 71% of Earth's surface, holding 97% of all the planet's water. That's approximately 326 million trillion gallons of water, if you can even comprehend a number that large. And in all that water, in all that vastness, we've only explored about 5% of it. 5%. That means 95% of the underwater world remains completely unexplored, unmapped, and unknown. What's down there in that other 95%? What creatures have evolved in total isolation, never seeing human eyes? What landscapes exist in the perpetual darkness, shaped by forces we don't understand? Tonight, over the next several hours, we're going to explore some of the most compelling mysteries that we do know about. And if these are what exist in the 5% we've seen, imagine what horrors and wonders wait in the 95% we haven't. The ocean is not a uniform body of water. It's a layered cake of different zones, each with its own rules, its own inhabitants, its own secrets. The sunlight zone, or epipelagic zone, extends from the surface down to about 200 meters. This is where most of the life we're familiar with exists. The fish we eat, the coral reefs we photograph, the waters we swim in. But this is just the very surface of the story. Below that, from 200 to 1,000 meters, lies the twilight zone, or mesopelagic zone. Sunlight begins to fade here. Colors disappear one by one as you descend, and the temperature drops dramatically. This is where things start to get weird. Fish here have developed massive eyes to capture what little light exists, or they've evolved bioluminescence to create their own. They drift through the permanent dusk like ghosts, hunting and being hunted in the dim blue-gray world. Then comes the midnight zone, the bathypelagic zone, from 1,000 to 4,000 meters down. Total darkness reigns here. No sunlight has ever penetrated this deep, not a single photon. The pressure is crushing, the cold is intense, and yet life persists in forms so bizarre they seem almost fictional. Below that lies the abyssal zone, 4,000 to 6,000 meters deep. The abyss. This is where the word abyssal comes from, meaning bottomless, unfathomable. The temperature here is just above freezing, hovering around 2 to 3 degrees Celsius. The pressure is over 500 times what you experience at sea level. And still, there is life. strange, alien life that has never known anything but crushing pressure and eternal night. And finally, the deepest layer, the Hadal zone, named after Hades, the ancient Greek underworld. This zone includes all ocean trenches deeper than 6,000 meters. The Mariana Trench, the deepest point on Earth, reaches down to nearly 11,000 meters in its deepest spot, the Challenger Deep. At these depths, the environment is so extreme that it's closer to the conditions on other planets than anywhere else on Earth. And yet, when we send cameras down there, when we finally manage to reach these impossible depths, we find life. Not just bacteria or simple organisms, but fish, crustaceans, complex living creatures that thrive in conditions that should be utterly incompatible with life as we understand it. Let's talk about the Mariana Trench in more detail, because this is where our journey truly begins. The Mariana Trench is a crescent-shaped scar in the ocean floor, located in the western Pacific east of the Mariana Islands. It's over 1,500 miles long and 43 miles wide on average. But it's the depth that truly staggers the mind. At its deepest point, the Challenger Deep, the ocean floor sits 36,070 feet below the surface. That's nearly 7 miles straight down. If you stood at the bottom of the Challenger Deep and looked up, you wouldn't see light. You wouldn't see anything. The water column above you would be so massive that it would block out any hint of the world above. You'd be standing in absolute, total, complete darkness. The pressure at that depth is approximately 16,000 pounds per square inch. To put that in perspective, that's like having 50 jumbo jets stacked on top of your thumbnail. The temperature is a steady 34 to 39 degrees Fahrenheit, just above freezing. And in 1960, 2 men actually went down there. Jacques Piccard and Don Walsh descended to the bottom of the Challenger Deep in a bathyscaphe called the Trieste. They spent 20 minutes on the ocean floor, looking out through a small porthole into the abyss. And what they saw would change our understanding of life on Earth. They saw a flatfish calmly swimming along the bottom, nearly 7 miles beneath the ocean surface. Life existed even there, in the most extreme environment on the planet. Since then, only a handful of people have made the journey to the bottom of the Mariana Trench. Director James Cameron made the descent in 2012, alone in a specially designed submersible. He described it as like being on another planet, a world utterly alien to anything we know. The bottom of the trench isn't smooth sand or rock. It's a thick layer of sediment accumulated over millions of years, made up of the remains of dead organisms that have drifted down from the surface. It's basically an underwater graveyard, a repository of death that stretches as far as the eye can see, if the eye could see anything in that darkness. But here's what makes the Mariana Trench truly terrifying from a mystery perspective. We've barely explored it. The handful of dives that have been made represent mere pinpricks in a massive underwater canyon system. We have better maps of Mars than we do of the Mariana Trench. What else lives down there? What else exists in the miles of trench that have never been visited by human eyes or cameras? Every expedition to the deep ocean brings back footage of new species, organisms that science has never catalogued. In 2014, an expedition to the Mariana Trench captured footage of a previously unknown species of snailfish. It was ghostly white, almost transparent, with a body that seemed too delicate to survive the crushing pressure. And yet there it was, thriving at depths where it shouldn't be possible. The fish had adapted to the pressure so completely that if you brought it to the surface, it would literally fall apart. Its cellular structure requires that immense pressure to maintain integrity. In 2016, Another expedition discovered amphipods in the Mariana Trench that were over 30 centimeters long. For reference, amphipods are usually the size of your fingernail. These were over a foot long, scuttling around in the darkness like aquatic cockroaches the size of house cats. They were feeding on wood that had fallen into the trench, remnants of trees and plants from the surface world. Even at 7 miles deep, nothing goes to waste in the ocean. But perhaps the most disturbing discovery in the Mariana Trench is something we put there ourselves. In 2019, explorer Victor Vescovo made a dive to the bottom of the Challenger Deep, and among the strange creatures and alien landscapes, he found something that turned his stomach: a plastic bag and candy wrappers. Human trash, sitting at the deepest point on planet Earth, in a place that should be pristine and untouched. It was a stark reminder that no place on Earth is beyond our reach or our impact. But it also raised disturbing questions. If our plastic can reach the deepest part of the ocean, what else has made it down there? What chemicals, what pollutants, what toxins have seeped into the last unexplored frontier on our planet? And what effect are they having on the bizarre life forms that exist in that alien world? The Mariana Trench is also home to mud volcanoes, underwater mountains that spew a thick mixture of mud, methane, and other gases from deep within the Earth's crust. These mud volcanoes create their own microenvironments, places where unique species have evolved to live off the chemicals and heat that emerge from the seafloor. Some of these mud volcanoes are massive, rising hundreds of feet from the ocean floor. They bubble and steam in the darkness like something from a nightmare landscape. And then there are the sounds. The ocean is not silent. It's full of sounds, some natural, some mysterious, some utterly terrifying. The Mariana Trench has been the source of some of the strangest sounds ever recorded in the ocean. Low-frequency moans that seem to come from nowhere and everywhere at once. Clicking sounds that repeat in patterns that seem almost deliberate. Rumbles and groans that suggest massive movements in the Earth's crust, or perhaps something else entirely. In 1997, NOAA detected a sound called the bloop in the Pacific Ocean. It was one of the loudest underwater sounds ever recorded, detected by sensors over 3,000 miles apart. The sound was consistent with something massive, something far larger than any known animal, rising rapidly from deep in the ocean and making some kind of vocalization. For years people speculated about what could have made such a sound. Was it an unknown sea creature, something so large that it dwarfed even blue whales? Was it something from the deepest trenches, emerging briefly to announce its presence before descending back into the abyss? Eventually, scientists determined that the bloop was most likely caused by an icequake, the sound of a massive iceberg cracking and breaking apart. But here's the unsettling part. That was their best guess. They can't be completely certain. And even if the bloop was an iceberg, it doesn't explain all the other sounds that have been detected in the deep ocean, sounds that don't match any known geological or biological source. The ocean is singing to us in a language we don't understand, and some of those songs sound like warnings. In 2022, researchers detected a series of sounds coming from the Hadal Zone that they described as metallic groaning. The sounds would build in intensity over several minutes, reach a crescendo that was almost painful to listen to, and then suddenly stop. Complete silence would follow for hours, and then the groaning would begin again. They still don't know what causes it. Some researchers believe it could be tectonic plates grinding against each other in the deep ocean floor. Others think it might be related to underwater volcanic activity that we haven't discovered yet. But there's a third group, a smaller group that doesn't like to speak too loudly about their theory. They think it might be biological. They think something down there, something massive, is making noise. Let's shift our focus from the depths to something equally mysterious but closer to the surface. The Bermuda Triangle. You've heard of it, everyone has. That roughly triangular area of the Atlantic Ocean between Miami, Bermuda, and Puerto Rico, where ships and planes supposedly vanish without a trace. Over the years, the Bermuda Triangle has become synonymous with unexplained disappearances and paranormal activity. But what's the reality behind the legend? The Bermuda Triangle covers approximately 500,000 square miles of ocean. That's a massive area, roughly the size of Alaska. And yes, ships and aircraft have disappeared there. But here's what most people don't tell you. Ships and aircraft disappear all over the world's oceans at similar rates. The Bermuda Triangle isn't statistically more dangerous than any other heavily traveled shipping route. But that doesn't mean there aren't mysteries there, because there are real, documented, utterly baffling mysteries that have nothing to do with paranormal activity and everything to do with the ocean being far stranger than we give it credit for. Let's talk about Flight 19. On December 5, 1945, 5 TBM Avenger torpedo bombers took off from Fort Lauderdale, Florida, on a routine training mission. The weather was good, the planes were in excellent condition, and the pilots were experienced. They were supposed to fly east, conduct bombing practice, and return. It should have been simple. But about an hour and a half into the flight leader, Lieutenant Charles Taylor, radioed back to base. His compasses weren't working, both of them. He thought they were over the Florida Keys, but he wasn't sure. Base tried to guide him back, but Taylor seemed increasingly disoriented. His radio transmissions became more confused, more panicked. Other pilots in the squadron reported that their compasses were also malfunctioning. They were spinning wildly, giving random readings. Without functioning compasses and with visibility decreasing as weather moved in, the squadron was flying blind. For hours, radio operators on the ground listened to the increasingly desperate transmissions from Flight 19. They could hear the pilots trying to figure out where they were, trying to navigate by landmarks they couldn't find. The last transmission from Flight 19 came around 7:04 p.m. After that, silence. 5 planes, 14 men, vanished. A massive search and rescue operation was launched immediately. And here's where it gets even stranger. One of the search planes, a PBM Mariner flying boat with a crew of 13, also disappeared. It took off to search for Flight 19 and was never seen again. So now we have 6 aircraft and 27 men missing. No wreckage was ever found. No bodies were ever recovered. No oil slicks. No debris fields. Nothing. It was as if they had simply ceased to exist. The official Navy report concluded that the planes had run out of fuel and crashed into the ocean, but that doesn't explain why no trace of them was ever found. The ocean in that area is deep, yes, but not impossibly so. And yet, despite decades of searching, despite modern technology, despite countless expeditions, Flight 19 remains lost. Some wreckage has been found over the years that people claimed might be from Flight 19, but in every case, it turned out to be from other aircraft that had crashed in the area at different times. The Bermuda Triangle, it turns out, has claimed more aircraft than just Flight 19. One of the proposed explanations for disappearances in the Bermuda Triangle is methane hydrates. Methane hydrate is a kind of ice that forms when methane gas gets trapped in frozen water under high pressure. It exists in massive quantities on the ocean floor in certain areas, including parts of the Bermuda Triangle. Under the right conditions, this methane hydrate can suddenly destabilize and release huge amounts of methane gas into the water. When methane gas bubbles up through the ocean, it reduces the density of the water. A ship floating in water that suddenly fills with methane gas bubbles will lose buoyancy. It will sink, and it will sink fast. There wouldn't be time for a distress call. The ship would just drop like a stone, swallowed by the ocean in seconds. And once it's down, the methane dissipates, the water returns to normal, and there's no evidence of what happened. This could also affect aircraft. Large releases of methane gas can rise into the atmosphere, creating pockets of air with significantly different density than normal. An aircraft flying into such a pocket could experience sudden loss of lift, stalling the engines, or causing the plane to drop out of the sky. It's a plausible scientific explanation for at least some of the disappearances, but it doesn't explain everything. It doesn't explain the compass malfunctions reported by Flight 19. It doesn't explain why some ships have been found drifting empty in the Bermuda Triangle. Their crews vanished, but the vessels intact. These are the cases that really chill the blood. Ships found with meals still warm on the table, coffee cups half full, no signs of struggle or distress, just empty. The Carroll A. Deering is one such case. In 1921, this 5-masted schooner was found run aground off the coast of North Carolina, just outside the traditional boundaries of the Bermuda Triangle, but close enough to be associated with it. When rescue crews boarded the ship, they found it completely abandoned. The crew's personal belongings were still there. The ship's log was missing. The lifeboats were gone. But there was no indication of why the crew had abandoned ship. The weather had been fine. The ship was seaworthy. There was no damage that would necessitate abandoning ship. Food was still in the galley, ready to be served. The crew had simply vanished. No bodies were ever found. No lifeboats were ever recovered. To this day, nobody knows what happened to the 11 crew members of the Carroll A. Deering. Then there's the curious case of the Ellen Austin, a schooner that in 1881 encountered a derelict ship in the Bermuda Triangle. The Ellen Austin pulled alongside the mystery vessel and found it in perfect condition but completely abandoned. The cargo was intact. There were signs that the crew had left in a hurry, but no indication of why. The captain of the Ellen Austin made a decision. He would put a prize crew aboard the derelict and sail both ships to port. For 2 days, the ships sailed together. Then a storm separated them. When the weather cleared and the Ellen Austin found the derelict again, something chilling had happened. The prize crew was gone. The men who had boarded the ship just 2 days earlier had vanished. According to some versions of the story, the captain of the Ellen Austin, either incredibly brave or incredibly foolish, put another crew aboard the derelict. The ship separated again in fog. The derelict was never seen again, and the second prize crew vanished along with it. Are these stories true? The historical record is murky, and details have definitely been embellished over the years. But something happened out there in 1881, something strange enough to be recorded and remembered. The ocean keeps its secrets, and the Bermuda Triangle seems to keep more than most. But perhaps the most unsettling thing about the Bermuda Triangle isn't the disappearances. It's the survivors, the people who have experienced strange phenomena in that area and lived to tell about it. Bruce Gernon is one such person. In 1970, Gernon was piloting a small aircraft through the Bermuda Triangle when he encountered what he describes as an electronic fog. According to Gernon, he was flying at about 11,000 feet when a strange cloud formation appeared ahead of him. The cloud was tunnel-shaped and seemed to be pulsing with light. Against his better judgment, he flew into it. Inside the cloud, his instruments went haywire. The compass spun wildly, his electronic equipment flickered and failed. But strangest of all, everything outside the aircraft seemed to disappear. He couldn't see the ocean below, couldn't see the sky above, just swirling grey fog that seemed to glow with its own internal light. The tunnel of cloud seemed to be moving with his aircraft, keeping him enclosed. Gannon estimated he was in the fog for about 10 minutes. When he emerged, he found himself directly over Miami Beach. The problem was, based on his flight time and speed, he should have still been at least 30 minutes away from Miami. He had somehow covered a distance that should have been impossible in the time that had elapsed. When he landed and checked with air traffic control, they confirmed something strange had happened. His plane had disappeared from radar for the exact amount of time he was in the fog. Gannon has spent decades trying to understand what happened to him that day. He's written books about it, given interviews, consulted with scientists. Some researchers think he might have experienced a rare atmospheric phenomenon, perhaps some kind of electromagnetic disturbance. Others think he experienced a time slip, a brief journey through a wrinkle in space-time. Gannon himself doesn't know what to believe. All he knows is that something impossible happened to him in the Bermuda Triangle, and he's spent the rest of his life trying to make sense of it. The Bermuda Triangle may not be the death trap of legend, but it is a reminder that the ocean is full of phenomena we don't understand. Electromagnetic anomalies, rapid weather changes, underwater topography that can create rogue waves and dangerous currents. The ocean doesn't need to be supernatural to be deadly. Its natural behavior is mysterious enough. Let's move from mysterious disappearances to mysterious appearances. Because sometimes the ocean doesn't just take things away. Sometimes it brings things back, or brings things up from the depths that were never meant to see the light of day. Ghost ships are a maritime phenomenon that has been documented for centuries. These are vessels found adrift with no crew, no explanation, no sign of what happened. We've already discussed a few, but there are dozens more throughout history. Some of them can be explained by mutiny, piracy, or natural disasters, but others remain utterly baffling. The Orang Medan is perhaps the most disturbing ghost ship story of the 20th century. In June 1947, multiple ships in the Strait of Malacca picked up a distress signal. The message was chilling in its simplicity. All officers, including captain, are dead, lying in chart room and bridge, possibly whole crew dead. This was followed by indecipherable Morse code, and then a final message: I die. The Silver Star, an American merchant ship, was nearby and responded to the distress call. They found the Orang Medan drifting in the water. When they boarded, they discovered a scene from a nightmare. The entire crew was dead. The captain was on the bridge. The officers were in the chart room. The engineers were in the engine room. All dead. But it was the manner of their deaths that was so disturbing. According to the boarding party, the dead men's faces were frozen in expressions of absolute terror. Their eyes were wide open, staring at something unseen. Some were pointing at the sky. Others seemed to have died mid-scream. But there were no wounds, no signs of violence, no indication of what had killed them. Even the ship's dog was found dead, frozen in a snarl. The boarding party from the Silver Star decided to tow the Orang Medan to port. But before they could secure the tow lines, smoke began billowing from the hold of the ghost ship. The boarding party barely had time to get back to their own vessel before the Orang Medan exploded. The ship sank quickly, taking all evidence of what had happened with it to the bottom of the ocean. What killed the crew of the Orang Medan? Theories range from carbon monoxide poisoning to pirates to a cargo of illegal chemical weapons that leaked. Some researchers believe the ship was carrying potassium cyanide or nitroglycerin, which could have released toxic fumes that killed the crew rapidly. But here's the problem with that theory. Carbon monoxide and most toxic gases don't cause the kind of facial distortion described by the witnesses. They don't freeze expressions of terror onto dead faces. Some people think the whole story is a hoax, a maritime legend that grew in the telling. But records from both the Silver Star and other ships in the area that day do seem to corroborate that something happened. A ship was found adrift. A ship did explode and sink. Whether the details about the crew's expressions are accurate or embellished, we'll never know. The Orang Medan took its secrets to the bottom of the Strait of Malacca. Another ghost ship mystery involves the Joyita, found adrift in the South Pacific in 1955. The Joyita was a merchant vessel that had set sail from Samoa to the Tokelau Islands, a journey that should have taken about 2 days. The ship was carrying 25 people, crew and passengers, along with cargo. When it was found adrift weeks later, it was partially submerged, but still afloat, and it was completely empty. The strange thing about the Joyita was that it was unsinkable. The hull was lined with cork, making it practically impossible to sink even if damaged. And it was damaged. There was a hole in the hull, but not enough to sink the ship. The pumps could have easily handled the flooding. So why had everyone abandoned ship? The life rafts were gone, suggesting the crew and passengers had left intentionally. But why? The Joyita was found only 600 miles from its departure point, still well within range of rescue. Radio equipment was found on board, tuned to the international distress frequency, but the cable had been damaged. Whether it was damaged before or during the evacuation, nobody knows. Bloodstained bandages were found in the ship's cabin, suggesting someone had been injured. The ship's log, navigation equipment, and firearms were all missing, but cargo was still in the hold, and there was no sign of piracy. Whatever happened, it had caused 25 people to abandon a floating ship and take their chances in life rafts in the middle of the Pacific Ocean. None of them were ever found. No bodies, no rafts, no survivors. The official investigation concluded that the Joyita had probably been in a collision, possibly with a whale or another vessel, and that the crew had panicked and abandoned ship unnecessarily. But that doesn't explain the missing equipment, the blood, or why experienced sailors would make the fatal decision to leave a floating ship. The ocean is full of these ghost ships, vessels that tell the beginning of a story but never the end. And sometimes the ocean gives up ships that have been lost for decades or even centuries. In 2016, a sailor off the coast of Mindanao in the Philippines photographed what appeared to be a German U-boat from World War II floating on the surface. The submarine was covered in rust and barnacles, clearly having been underwater for decades. By the time authorities could investigate, the submarine had disappeared again, sinking back into the depths. Was it a U-boat? If so, which one? Over 700 German U-boats were lost during World War II, many in known locations, but many others simply vanished. Could one of them have been trapped in an underwater current for 70 years, only to be released briefly before sinking again? The ocean is constantly moving, constantly changing. Currents can trap objects and hold them for years before releasing them. Underwater landslides can uncover wrecks that have been buried for centuries. In 2001, a Swedish exploration team found what they claimed was a massive circular object on the floor of the Baltic Sea. The object, dubbed the Baltic Sea Anomaly, appeared to be about 200 feet in diameter, with smooth angular features that looked almost artificial. Some people immediately claimed it was a UFO that had crashed into the sea thousands of years ago. More rational explanations included unusual rock formations or the remnants of an ancient meteor impact. The team returned to the site multiple times to investigate. They reported strange electrical disturbances when they got close to the object. Cameras would fail, satellite phones would stop working. When they were directly above the object, all their electronic equipment would malfunction, move away, and everything would work perfectly again. Geologists who have studied the images say it's probably just glacial deposit, rocks and sediment left behind by moving ice during the last ice age. But the people who have actually been to the site aren't so sure. They describe the object as having features that seem too regular, too geometric to be natural. There are what appear to be straight edges, right angles, circular patterns. One diver described it as looking like the Millennium Falcon from Star Wars. To this day, the Baltic Sea anomaly remains unexplained. Most scientists think it's natural, but nobody can say for certain without more extensive investigation. And that's the thing about ocean mysteries. Even when we find something, even when we can dive down and look at it with our own eyes, we still can't always explain it. The ocean is an alien environment, and things that form naturally underwater can look bizarre and artificial to our land-dwelling eyes. But sometimes, just sometimes, we find things underwater that genuinely shouldn't be there. Off the coast of Japan, there's a formation known as the Yonaguni Monument. Discovered in 1986 by a dive tour operator, the Yonaguni Monument is a massive underwater rock formation that looks startlingly like a step pyramid. It has flat terraces, straight edges, right-angle corners, and even what appear to be carved faces and symbols. The monument is over 150 feet long and about 75 feet tall, sitting on the ocean floor, about 75 feet below the surface. The big question is whether the Yonaguni Monument is natural or man-made. Some geologists insist it's a natural formation created by tectonic activity and erosion over millions of years. The rock in that area, they say, naturally fractures along straight lines, creating the appearance of artificial construction. But other researchers, including some marine geologists, aren't so sure. They point to features that seem too regular, too purposeful to be natural. There are what appear to be roads, channels that look like they were carved to divert water, and flat areas that could have been used as foundations for buildings. There's even what looks like a carved face, similar to the Moai statues of Easter Island. If the Yonaguni Monument is artificial, it would rewrite our understanding of human history. The last time that area was above water was over 10,000 years ago, at the end of the last ice age. If humans built the monument, they did so before the rise of known civilizations like Sumer or ancient Egypt. The debate continues, with researchers on both sides presenting evidence and arguments. What's not in debate is that the Yonaguni Monument is there, underwater, waiting. Whether it's a natural wonder or a lost piece of prehistoric civilization, it's a reminder that the ocean floor holds secrets we're only beginning to discover. And if there's one monument, could there be others? How many lost civilizations might be lying beneath the waves, buried under sediment and coral? The ocean has a way of preserving things. In the cold, dark depths, with little oxygen and no sunlight, objects can remain intact for thousands of years. Ancient shipwrecks are found in the Mediterranean that look like they sank yesterday, their cargo still stacked neatly in the hold. In the Black Sea, where the deep water is anoxic and devoid of life, researchers have found perfectly preserved wooden ships over 2,000 years old. The wood hasn't rotted, the ropes are still tied in their original knots. If wooden ships can last that long, what else might be down there? What cities, what temples, what monuments to forgotten peoples? The ocean is humanity's attic, full of things we've lost and forgotten, and every now and then it gives something back. Let's talk about the sounds of the ocean again, because this is where things get truly eerie. The ocean is alive with sound. Whales sing to each other across thousands of miles. Dolphins click and whistle in complex patterns that might be language. Shrimp snap their claws to communicate and hunt. Fish grunt, croak, and hum. The ocean is never silent. But among all these biological sounds, there are others, sounds that don't match any known source. We've talked about the bloop, but there are many others. The upsweep is a sound that has been detected in the Pacific Ocean since 1991. It's a long, slow rising tone that happens seasonally, peaking in spring and fall. Scientists think it might be related to volcanic activity on the ocean floor, but they can't pinpoint the exact source. The upsweep changes over time, sometimes getting louder, sometimes fading. It's always there, though, humming away in the deep Pacific. A few years ago, it suddenly got much louder, prompting concerns that a major underwater volcanic event was about to occur. Then it faded back to normal levels. Nothing happened. The ocean was just making noise. Then there's the Julia sound, recorded in 1999. It was a loud, complex sound that lasted for about 15 seconds. Triangulation suggested it came from somewhere near the Antarctic, possibly near the Bransfield Strait. The sound was strong enough to be detected by sensors over 3,000 miles away. Analysis of the sound showed it had characteristics consistent with ice-related activity, possibly a massive iceberg scraping along the ocean floor or fracturing. But here's the thing. The Julia sound also had characteristics that were eerily similar to biological sounds. There were modulations, variations in pitch and tone that sounded almost like a voice. A very, very large voice. Some researchers have speculated that Julia might have been a massive iceberg, yes, but vibrating in such a way that it produced sounds similar to vocalization. Others prefer to think it was something biological, something immense living in the Antarctic waters. We know that blue whales can grow to over 100 feet long and weigh 200 tons. They're the largest animals known to have ever existed on Earth. But what if they're not the largest? What if there are creatures in the deep ocean that we haven't discovered yet? Creatures even larger than blue whales. The ocean is vast enough to hide them, and the deep ocean provides enough food through whale falls and other organic matter to sustain enormous life forms. Whale falls, for those who don't know, are the carcasses of dead whales that sink to the ocean floor. When a whale dies in the deep ocean, its body creates an entire ecosystem. The carcass can sustain life for decades, providing food for thousands of organisms. First come the scavengers, sharks and hagfish that strip the soft tissue. Then come the smaller creatures that feed on the bones and leftover scraps. Eventually, bacteria colonize the skeleton, feeding on the lipids in the bones themselves. A single whale fall can support a diverse community of life for 50 years or more. Now imagine something larger than a whale dying and falling to the ocean floor. It could sustain an ecosystem for centuries. And if such creatures exist, they would spend most of their time in the deep ocean, only rarely coming close enough to the surface to be detected. There would be ghosts, legends, monsters that exist just beyond the reach of our technology. In 2014, a commercial fishing vessel off the coast of Greenland detected something massive on their sonar. The object was moving, it was biological, and it was at least twice the size of a blue whale based on the sonar return. The crew tried to get a visual confirmation, but whatever it was stayed just deep enough to avoid being seen clearly. They followed it for nearly an hour before it descended into water too deep for their sonar to track. What was it? A blue whale can look larger on sonar than it actually is under certain conditions. But the crew of that fishing vessel were experienced mariners who had seen countless whales on sonar. They insisted this was different, larger, moving differently. Could it have been a group of whales swimming close together, creating the illusion of a single massive creature? Possibly. Or could it have been something we haven't discovered yet? The thing is, we keep finding new species in the ocean. Not just small fish or invertebrates, but large animals. In 2003, researchers discovered a new species of whale, the Perrin's beaked whale, from a specimen that washed up on a beach. In 2021, a new species of blue whale was identified through acoustic analysis of their songs. They were hiding in plain sight all along. We just didn't realize they were a separate species. If we can overlook entire species of whales, what else are we missing? What swims in the deep ocean, too shy or too rare to be captured on camera? What lurks in the midnight zone, hunting in the eternal darkness? The ocean is full of life we haven't documented, creatures that exist in ecosystems we barely understand. Take the giant squid, for example. For centuries, giant squid were thought to be legends, sailors' tales of monstrous kraken that could drag ships to the bottom of the ocean. But they were real. We just didn't have proof until we found their bodies washing up on beaches and recovered them from the stomachs of sperm whales. Even then, seeing a live giant squid in its natural habitat remained impossible for decades. It wasn't until 2004 that researchers finally captured the first photographs of a live giant squid in the wild. And it wasn't until 2012 that we got video footage of one in its deep ocean habitat, a creature that can grow up to 43 feet long, with eyes the size of dinner plates, and we didn't see one alive in the wild until 2012. That's how good the ocean is at keeping secrets. And giant squid aren't even the largest squid species. That title belongs to the colossal squid, an even more mysterious creature that lives in the deep waters around Antarctica. Colossal squid can grow even larger than giant squid, with some specimens estimated to reach 46 feet or more. They have hooks on their tentacles in addition to suckers, rotating hooks that can swivel and grip prey. They live at depths where the pressure is crushing and the cold is intense. We've never seen a live colossal squid in its natural habitat. Every specimen we've examined has been dead, either caught in fishing nets or found in the stomachs of sperm whales. Sperm whales dive deep to hunt squid, and the battle scars on some sperm whales suggest they're fighting creatures of truly impressive size. Whales have been found with sucker scars over a foot in diameter, suggesting squid far larger than any specimen we've recovered. What's down there in the deep ocean, hunting and being hunted? What creatures have evolved to survive in conditions so extreme that we can barely imagine them? The ocean's food chains don't work like land food chains. On land, you need sunlight for plants, plants for herbivores, herbivores for predators. But in the deep ocean, there is no sunlight. The entire ecosystem is based on organic matter falling from above, on chemosynthesis around volcanic vents, on cycles of life and death that are completely alien to land dwellers. And in those alien ecosystems, nightmares live. The anglerfish is a prime example. Female anglerfish live in the deep ocean, using a bioluminescent lure to attract prey in the darkness. They have massive jaws filled with needle-like teeth that point inward, ensuring that anything that enters the mouth can never escape. They can swallow prey up to twice their own size by unhinging their jaws like a snake. But the truly disturbing part is how they reproduce. Male anglerfish are much smaller than females, and when a male finds a female, he bites into her flesh and fuses with her body. Over time, he loses his eyes, his internal organs, everything. He becomes a parasitic appendage, nothing more than a source of sperm for the female. Multiple males can attach to a single female, creating a chimeric creature that is part female, part male, a fusion of multiple organisms into one. The viperfish is another deep-sea nightmare. It has teeth so long that it can't close its mouth completely. The teeth curve back toward its eyes, ensuring that anything it bites is impaled on multiple needles. Viperfish use bioluminescence to attract prey, flashing lights along their bodies to confuse and lure smaller fish in the darkness. When something gets close enough, the viperfish strikes with incredible speed, its jaws snapping shut with enough force to pierce through scales and bone. The fangtooth fish has the largest teeth proportional to body size of any fish in the ocean. Its teeth are so large that it has special sockets in its skull to accommodate them when its mouth is closed. Otherwise, the teeth would pierce through its own brain. It lives at depths of up to 16,000 feet, hunting in total darkness, using its lateral line system to detect vibrations in the water. These creatures look like monsters, but they're perfectly adapted to their environment. In the deep ocean, being terrifying is an advantage. Extreme adaptations mean you can catch prey that other predators can't. You can survive in conditions that other creatures can't tolerate. The deep ocean is an arms race, a constant evolutionary pressure to become stranger, more specialized, more deadly. And we've only catalogued a tiny fraction of the species that exist down there. Every deep-sea expedition brings back footage of creatures that science has never seen before. In 2019, a submersible expedition to the deep ocean near the Mariana Trench captured footage of a jellyfish unlike anything ever documented. It was enormous, over 100 feet across, with tentacles that seemed to go on forever into the darkness. The creature was almost transparent, glowing faintly with bioluminescence. It moved slowly through the water, its tentacles trailing behind it like a living net. What was it? How long does it live? What does it eat? How does it reproduce? We don't know. We saw it once for a few minutes, and then it disappeared back into the darkness. That's all we have. A brief glimpse of something that might be rare or might be common in parts of the ocean we've never visited. The ocean is full of these brief glimpses, these momentary encounters with the unknown. In 2018, researchers in the deep Pacific Ocean discovered what they call swimming worms. These aren't worms in the traditional sense. They're massive, over 6 feet long, and they move through the water by undulating their entire bodies. They're covered in transparent flesh, and you can see their internal organs through their skin. They appear to be predators, though what they hunt and how they hunt is a mystery. No one knew these creatures existed until high-definition cameras were deployed in the deep ocean. They've probably been swimming around down there for millions of years, completely unnoticed by humans. What else is down there that we haven't seen yet? What other impossible creatures are living their lives in the eternal night of the deep ocean? Let's shift gears and talk about something that sounds like science fiction but is absolutely real. Underwater avalanches. Most people don't realize that the ocean floor isn't static. It's constantly changing, constantly moving, constantly reshaping itself. And sometimes massive amounts of sediment can suddenly break loose and flow down underwater slopes at incredible speeds. These underwater avalanches are called turbidity currents, and they're one of the most powerful forces in the ocean. A major turbidity current can move millions of tons of sediment at speeds of up to 60 miles per hour. They can travel for hundreds of miles across the ocean floor, carving out massive channels and canyons, and they can happen without warning. In 1929, a magnitude 7.2 earthquake struck the Grand Banks off the coast of Newfoundland. The earthquake itself caused damage on land, but it was what happened underwater that was truly devastating. The earthquake triggered a massive turbidity current that flowed down the continental slope and across the abyssal plain. The current was so powerful that it snapped undersea telegraph cables one by one as it raced across the ocean floor. Scientists were able to calculate the speed of the turbidity current by noting when each cable broke. The current was moving at approximately 60 miles per hour, carrying an estimated 100 cubic kilometers of sediment. For comparison, that's enough sediment to bury Manhattan under a layer of mud 300 feet deep. The turbidity current traveled over 400 miles before finally dissipating. These underwater avalanches are powerful enough to destroy anything in their path. Submarines caught in a turbidity current would be swept away and potentially crushed by the sheer mass of moving sediment. Underwater installations, pipelines, cables, all vulnerable, and we can't predict when they'll happen. We know they're triggered by earthquakes, underwater landslides, and other geological events. But we can't always predict when those events will occur. The ocean floor is crisscrossed with submarine canyons, carved by ancient and modern turbidity currents. Some of these canyons are massive, rivaling the Grand Canyon in size and depth. The Monterey Canyon off the coast of California is over 150 miles long and reaches depths of 2 miles below sea level. It was carved primarily by turbidity currents over millions of years, and turbidity currents still flow down it today, reshaping it, deepening it, carrying sediment and organic matter to the deep ocean. But turbidity currents aren't the only underwater hazards that can appear without warning. Underwater landslides are another constant threat. The continental slopes, where the relatively shallow continental shelf gives way to the deep ocean, are steep and unstable in many places. Sediment accumulates over time, and eventually something triggers a collapse. The Storge slide, which occurred about 8,200 years ago off the coast of Norway, was one of the largest underwater landslides known to have occurred. It displaced an estimated 840 cubic miles of sediment, roughly 3,500 billion tons of earth. The slide triggered a tsunami that hit the coast of Norway and Scotland with waves up to 80 feet high. Evidence of the tsunami has been found miles inland, in the form of sediment deposits and disturbed geological layers. If a similar slide occurred today, it would be catastrophic. Millions of people live along the coasts that would be affected, and we know that the conditions for such slides still exist. The ocean floor is still accumulating sediment. Steep slopes still exist. Geological instability is still present. It's not a question of if another massive underwater landslide will occur, but when, and there are other geological hazards lurking in the ocean. Underwater volcanoes or seamounts are scattered across the ocean floor by the thousands. Many of them are extinct, dead volcanoes that erupted millions of years ago and have been dormant ever since. But many others are active, spewing lava and superheated water into the ocean. Some underwater volcanoes reach almost to the surface, creating navigation hazards and occasional islands. The island of Surtsey, off the coast of Iceland, was created by an underwater volcanic eruption in 1963. The volcano erupted with such force that it broke the surface of the ocean and created a new island where none had existed before. The eruption lasted for 3.5 years, building an island that's still there today. But most underwater volcanic eruptions occur in the deep ocean, far from human observation. We only know they're happening when we detect unusual seismic activity or when we stumble upon fresh lava flows during deep-sea expeditions. In 2015, researchers discovered an underwater volcano near the Mariana Trench that was actively erupting liquid sulfur. Not lava, sulfur. The volcano was spewing molten sulfur at temperatures of 187 degrees Celsius, creating pools of liquid sulfur on the ocean floor. This was something completely new to science. No one knew that underwater volcanoes could erupt sulfur, and yet there it was, creating an alien environment where life still managed to exist. Bacteria were thriving in the sulfur pools, feeding on the chemicals and heat. Small shrimp were living nearby, adapted to the extreme conditions. Life finds a way even in the most unlikely places. The ocean floor is dotted with hydrothermal vents, places where superheated water shoots up from cracks in the Earth's crust. These vents can reach temperatures of over 400 degrees Celsius, hot enough to melt lead. The water is filled with dissolved minerals and chemicals, toxic to most life on Earth. And yet, around these vents, entire ecosystems thrive. Giant tube worms grow up to 8 feet long, anchored to the rocks around the vents. They have no mouth, no digestive system, no way to eat. Instead, they have a symbiotic relationship with bacteria that live inside their bodies. The bacteria process the chemicals from the vent water and produce nutrients that the tube worms absorb. It's a completely alien form of life, based on chemosynthesis rather than photosynthesis. Yeti crabs cluster around the vents, their bodies covered in hair-like filaments that host bacteria. The crabs farm the bacteria, waving their arms through the vent water to feed the bacterial colonies, then harvesting the bacteria for food. Blind shrimp swarm in the superheated water, detecting the heat with special organs since their eyes are useless in the total darkness. This is life that doesn't need the sun, doesn't need oxygen in the traditional sense, doesn't follow the rules that govern ecosystems on the surface. When hydrothermal vents were first discovered in 1977, they revolutionized our understanding of life on Earth. If life could exist in such extreme conditions, then it could potentially exist in similar conditions on other planets. The moons of Jupiter and Saturn, like Europa and Enceladus, are thought to have liquid oceans beneath their icy surfaces. And if those oceans have hydrothermal vents, they might have life. Life based on the same chemosynthetic principles that support the ecosystems around Earth's underwater vents. The discovery of hydrothermal vents raised profound questions, not just about life on other planets, but about the origin of life on Earth. Some scientists now believe that life on Earth might have originated around hydrothermal vents in the ancient ocean. The chemical reactions occurring at the vents could have provided the energy and raw materials needed for the first primitive life forms to emerge. If so, then the deep ocean isn't just a weird environment where strange things live. It's the birthplace of all life on Earth. We are children of the abyss, descendants of organisms that first evolved in the crushing darkness of the deep ocean billions of years ago. Every cell in your body can trace its lineage back to those primitive bacteria living around hydrothermal vents when the Earth was young. The ocean is in our DNA, quite literally. But let's get back to mysteries, because the ocean has plenty more to offer. Let's talk about bioluminescence, the ability of organisms to produce their own light. On land, bioluminescence is relatively rare. Fireflies, some fungi, certain bacteria. But in the ocean, especially in the deep ocean, bioluminescence is everywhere. It's estimated that up to 90% of organisms living in the deep ocean have some form of bioluminescence. They use it for a variety of purposes: attracting prey, confusing predators, communicating with each other, finding mates. The deep ocean is alive with biological light, a light show that happens in total darkness where no human eyes can see it. Some bioluminescent organisms produce a steady glow. Others can flash or pulse their light in complex patterns. The hatchetfish has light-producing organs on its underside that exactly match the faint light filtering down from above, making it invisible when viewed from below. It's natural camouflage, using light instead of color. The cookie-cutter shark uses bioluminescence in a devious way. Its belly glows with bioluminescent light, but there's a dark patch near its throat that doesn't glow. From below, the shark looks like a small fish, the dark patch appearing to be the fish's silhouette. Larger predators attack what they think is an easy meal, only to have the cookie-cutter shark whip around and bite a chunk out of them with its circular mouth of serrated teeth. The shark gets a meal, and the larger fish is left with a distinctive circular wound. Many jellyfish are bioluminescent, creating displays of light as they pulse through the water. Some can produce waves of light that travel across their bells, possibly to startle predators or attract prey. The crystal jellyfish produces green fluorescent protein, or GFP, which has become one of the most important tools in molecular biology. Scientists can insert GFP into cells to track processes, visualize structures, and study biological functions, all because a jellyfish in the Pacific Ocean evolved the ability to glow green. But perhaps the most mysterious aspect of bioluminescence is how coordinated it can be. There are reports, mostly from sailors and ocean voyagers, of massive bioluminescent events, entire stretches of ocean that suddenly light up with billions of bioluminescent organisms all triggering at once. These events, sometimes called milky seas, create an eerie glow that can extend for miles. In 1995, a British merchant ship reported sailing through a milky sea in the Indian Ocean. The glow was so bright that the crew could clearly see their ship's wake in the water, glowing white against the luminescent sea. The event lasted for several hours and covered an estimated 6,000 square miles of ocean. Satellite imagery later confirmed the event, detecting an unusual glow emanating from the ocean surface. What causes milky seas? The leading theory is that they're caused by massive blooms of bioluminescent bacteria, possibly triggered by specific oceanic conditions. But why the bacteria all trigger their bioluminescence at the same time, creating a coordinated light show, remains unknown. Are they communicating? Are they responding to some environmental cue we don't understand? Or is it just a random coincidence that millions of bacteria happen to glow at the same time? The ocean is full of these light shows that humans rarely witness. In 2012, sailors in the Indian Ocean reported something even stranger, a massive underwater glow that moved beneath their ship, staying with them for over an hour. The glow was deep, well below the surface, and it pulsed rhythmically. It wasn't coming from the surface. It was coming from something deep down. The sailors described it as looking like they were sailing over a massive bioluminescent creature, something huge, keeping pace with their ship in the deep water. They could see the glow undulating, changing intensity, moving in ways that seemed almost purposeful. Then, as suddenly as it appeared, it vanished. The glow faded, and the ocean returned to its normal darkness. What was it? A school of bioluminescent squid, perhaps, swimming together in a massive cluster? Some kind of jellyfish bloom, millions of individuals creating a collective glow? Or something else, something we don't have a name for yet? The ocean keeps its secrets. And this is one more mystery to add to the collection. Let's talk about ocean currents, because they're far stranger than most people realize. The ocean is constantly moving, driven by temperature differences, salinity differences, wind, and the Earth's rotation. These movements create currents, rivers within the ocean that flow with incredible power. The Gulf Stream, for example, is a massive current that flows from the Gulf of Mexico up the eastern coast of North America and across the Atlantic to Europe. It moves about 100 million cubic meters of water per second. That's more than all the rivers on Earth combined. The Gulf Stream is so powerful and so consistent that it affects the climate of entire continents. Without the Gulf Stream, Europe would be much colder, perhaps uninhabitable in parts. But ocean currents aren't just surface phenomena. There are deep ocean currents that flow along the bottom of the ocean, moving cold, dense water from the poles toward the equator. These deep currents are part of a global conveyor belt system that regulates Earth's climate. Water sinks in the polar regions, flows along the ocean floor for thousands of miles, then rises and returns to the poles to complete the cycle. This process takes about 1,000 years for a complete circuit. The thing is, we don't fully understand how this system works. We know the basic mechanics, but the details are murky. Small changes in temperature or salinity can dramatically affect current patterns. And if the currents change, the climate changes with them. There's evidence that ocean current patterns have shifted dramatically in Earth's past, triggering rapid climate changes. The Younger Dryas period, about 12,000 years ago, saw temperatures drop dramatically in the northern hemisphere in just a few decades. The leading theory is that melting glaciers dumped so much fresh water into the North Atlantic that it disrupted the ocean current system. The Gulf Stream weakened or shifted. Europe and North America plunged back into Ice Age conditions, and the brief warming period that had been underway came to an abrupt halt. It lasted for over 1,000 years before the currents re-established themselves and warming resumed. But it's a stark reminder of how dependent we are on the ocean's current systems. If they change again, if something disrupts the delicate balance of temperature and salinity that drives them, the climate consequences could be catastrophic. Ocean currents can also create some truly bizarre phenomena. Rogue waves, for example, are massive waves that appear seemingly out of nowhere, tower over the surrounding ocean, and then disappear just as suddenly. For years, rogue waves were considered sailors' legends, waves that tall oceanographers said were statistically impossible. The ocean simply didn't work that way. Then, in 1995, a laser rangefinder on an oil platform in the North Sea recorded a wave that was 84 feet tall. The surrounding waves were about 40 feet, which was already rough. But this single wave was twice as tall as anything around it, a moving mountain of water that appeared, passed beneath the platform, and vanished. The Drupner wave, as it came to be known, proved that rogue waves were real. Since then, we've detected hundreds of rogue waves using satellite technology and shipboard instruments. We now know they're much more common than previously thought. But we still don't fully understand how they form. The leading theories involve wave interference patterns, where multiple waves combine at just the right moment to create a single massive wave. Ocean currents can also play a role, concentrating wave energy in specific areas. But rogue waves remain largely unpredictable. They can occur in any ocean, in any weather conditions. Ships have been sunk by rogue waves, massive freighters that one moment were sailing along normally and the next were capsized by a wall of water that came out of nowhere. The MS München, a German cargo ship, disappeared in the Atlantic in 1978. A massive search found only a few pieces of wreckage, including a lifeboat that had been mounted 65 feet above the waterline. Something had ripped that lifeboat off the ship. The leading theory is that a rogue wave, possibly over 100 feet tall, struck the ship and sank it in minutes. The ocean is full of dangers that we can't predict or control. Rogue waves, underwater landslides, sudden storms that form in hours and dissipate just as quickly. The ocean doesn't care about human plans or safety precautions. It operates according to its own rules, rules we're still trying to understand. There's a place in the Pacific Ocean called the White Shark Cafe. It's not a cafe in any traditional sense. It's a region of open ocean halfway between Baja California and Hawaii, where great white sharks congregate every year. For decades, researchers knew that great white sharks migrated long distances, but they didn't know where they went or why. Then satellite tagging technology revealed something unexpected. Great white sharks from the coast of California would swim out into the middle of the Pacific Ocean to this specific area and spend months there. They would dive deep, sometimes over 1,000 feet down, then return to the surface. This behavior would repeat, day after day, week after week. But here's the mystery. There doesn't appear to be much food in the White Shark Cafe. It's a relatively barren stretch of open ocean, so why do the sharks go there? Initially, researchers thought it might be a mating area, but both male and female sharks exhibit the same deep diving behavior, which doesn't fit typical mating patterns. The leading theory now is that the sharks are feeding on something in the deep scattering layer. The deep scattering layer is a phenomenon detected by sonar, a layer of the ocean that appears solid on sonar, but is actually made up of billions of small organisms. Fish, squid, jellyfish, all clustering together at depth during the day, then rising toward the surface at night to feed. The deep scattering layer in the White Shark Cafe area might be particularly dense or might contain prey species that the sharks favor. But we can't be certain, because we can't observe what the sharks are doing when they dive. We can track where they go, how deep they go, but we can't see what they're doing down there. Are they feeding? Are they socializing? Is there some other behavior we haven't even considered? The sharks keep returning to the White Shark Cafe every year, following a schedule that varies slightly, but is remarkably consistent. They know something about that area of the ocean that we don't, and until we can follow them down into the deep scattering layer and observe their behavior directly, it remains a mystery. Great white sharks are apex predators, sitting at the top of the ocean food chain, but even they have things to fear in the ocean. Orcas, or killer whales, have been observed hunting and killing great white sharks. The orcas have developed a technique where they flip the shark upside down, inducing tonic immobility, a paralyzed state that some sharks enter when inverted. Once the shark is immobilized, the orcas kill it and eat its liver, which is rich in nutrients. In 2017, 5 great white sharks washed up on beaches in South Africa within a few months, all with their livers removed with surgical precision. Orcas were responsible, and after those kills, the great white shark population in that area of South Africa dropped dramatically. The sharks fled, abandoning their traditional hunting grounds. The presence of orcas had so thoroughly terrified them that they'd rather go somewhere with less food than risk encountering the killer whales. Orcas are incredibly intelligent and social animals. They hunt in coordinated groups, communicate with complex vocalizations, and pass knowledge down through generations. Different populations of orcas have different cultures, different hunting techniques, even different dialects in their vocalizations. Some orca populations specialize in hunting fish, others in hunting seals and sea lions, others in hunting whales. The whale-hunting orcas are perhaps the most impressive. They work together to isolate a whale calf from its mother, then attack it relentlessly until it drowns. Or they'll attack larger whales, biting and ramming until the whale is too exhausted to continue swimming. The hunt can last for hours, a brutal test of endurance and coordination. There have been very few documented cases of orcas attacking humans in the wild. Despite their name, killer whales, they seem to recognize that humans aren't prey. But there have been incidents where orcas have behaved aggressively toward boats. In 2020 and 2021, a group of orcas off the coast of Spain and Portugal began ramming boats, specifically targeting the rudders. They would swim up to sailboats and repeatedly strike the rudder, sometimes causing enough damage to disable the boat. Researchers were baffled. This wasn't typical orca behavior. Some speculated that a young orca had been injured by a boat propeller and was now teaching other orcas to attack boats in retaliation. Others thought it might be playful behavior that had gotten out of hand. But the attacks were too coordinated, too focused to be simple play. The orcas seemed to know exactly what they were doing. They would target the rudder specifically, the most vulnerable part of a sailboat's steering system, and they would work together, taking turns ramming the rudder until it broke. It was strategic, intelligent behavior, and it was deeply unsettling to the sailors who experienced it. What makes an orca decide to attack a boat? What communication happens among the pod that leads to coordinated behavior like this? We know orcas are intelligent, but the extent of their intelligence and the complexity of their social structures remain largely mysterious. They're using sonar to map their environment in ways we don't fully understand. They're communicating with sounds that range from simple calls to complex songs, and they might be aware, in some way we can't quite define, of their place in the ocean ecosystem. They might understand that they're apex predators, that they have nothing to fear except other orcas. They might have a sense of self, of family, of history. We just don't know. The ocean is full of intelligent life, and we're only beginning to scratch the surface of understanding it. Now let's talk about something that might sound mundane, but is actually crucial: ocean mapping. We've mentioned that we've mapped less than 20% of the ocean floor in detail. The rest is known only from satellite measurements and sonar pings that give rough estimates of depth. Why haven't we mapped the entire ocean floor? Because it's incredibly difficult and expensive. Satellite measurements can detect variations in the ocean surface that indicate features on the seafloor, but the resolution is limited. You can detect major features like underwater mountains and trenches, but you can't see details. To create detailed maps, you need ships equipped with multi-beam sonar. These ships have to travel slowly over the ocean, sending out sonar pulses and listening for echoes. It takes time, it takes money, and there's a lot of ocean to cover. At the current rate of mapping, it would take hundreds of years to map the entire ocean floor in detail. Various international efforts are working to speed this up, with the goal of mapping the entire ocean by 2030. But that's an ambitious target. Why does it matter? Because we can't protect what we don't know exists. Underwater mountains, called seamounts, are hotspots of biodiversity, but we don't know where most of them are. Fishing vessels sometimes stumble upon them, dragging their nets across pristine ecosystems and destroying them. If we had detailed maps, we could identify areas that need protection. We could route shipping lanes to avoid sensitive habitats. We could understand ocean currents better, improve tsunami predictions, and locate resources more efficiently. The ocean floor is not flat and featureless. It's a landscape as diverse and complex as anything on land. There are mountain ranges that dwarf the Himalayas. There are valleys deeper than the Grand Canyon. There are volcanoes, canyons, plateaus, and plains. The Mid-Atlantic Ridge is a massive underwater mountain range that runs down the center of the Atlantic Ocean. It's where new ocean floor is being created as tectonic plates pull apart. Magma rises from the Earth's mantle, cools, and becomes new rock. The process is slow, only a few centimeters per year, but over millions of years, it's created an entire mountain range. The Mid-Atlantic Ridge breaks the surface in a few places, creating islands like Iceland. But most of it is underwater, a chain of mountains that most people don't even know exists. It's home to unique ecosystems, hydrothermal vents, where life thrives in conditions that seem impossible. And we've explored only tiny portions of it. Most of the Mid-Atlantic Ridge is completely unknown. What lives there? What geological processes are occurring? What discoveries wait to be made? The ocean floor is the last great frontier on Earth. We've climbed the highest mountains, explored the densest jungles, crossed the harshest deserts. But the ocean floor remains largely unknown. And with every expedition we send down into the depths, we realize just how much we don't know. In 2021, a research team exploring the Pacific Ocean stumbled upon an underwater mountain that had never been mapped. It rose over 3,000 feet from the seafloor, a massive geological feature that had somehow escaped detection. On its slopes they found over 20 species that were completely new to science. 20 species on a single seamount. And there are tens of thousands of seamounts scattered across the ocean floor. How many undiscovered species exist on these underwater mountains? How many ecosystems are thriving in places we've never visited? The numbers are staggering when you start to think about them. Scientists estimate there might be over 2 million species living in the ocean, but we've only catalogued about 250,000. That means we haven't even discovered 90% of ocean life. 90%. Every time we send a submersible down to the deep ocean, we see things we've never seen before. In 2019, researchers exploring the Heddle Zone captured footage of a fish with completely transparent skin. You could see right through its body to its skeleton and internal organs. The fish had no pigmentation whatsoever, having evolved in an environment where color serves no purpose. It drifted through the water like a ghost, barely visible even when the submersible's lights were shining directly on it. What evolutionary pressures led to such extreme transparency? How does the fish avoid predators when it can't hide through camouflage? Does it have other defense mechanisms we haven't observed yet? These are questions we can't answer with a brief video clip from a single encounter. The ocean is full of these questions, these mysteries that multiply every time we make a new discovery. Let's talk about something that sounds simple, but is actually deeply mysterious: fish migration. Many fish species migrate vast distances across the ocean, traveling thousands of miles between feeding grounds and spawning sites. Salmon are famous for returning to the exact stream where they were born, swimming upstream against powerful currents to spawn and die. But how do they find their way? For decades, scientists thought salmon used their sense of smell to navigate. They memorized the chemical signature of their natal stream as juveniles, then follow that scent back as adults. And while smell does play a role, it's not the whole story. Salmon also use the Earth's magnetic field to navigate across the open ocean. They have magnetite crystals in their tissues that act like biological compasses. But even more mysteriously, salmon can detect incredibly subtle variations in the magnetic field. The Earth's magnetic field isn't uniform. It has bumps and dips and unique patterns in different locations. Salmon create magnetic maps in their brains, memorizing the magnetic signature of their birth stream. Years later, after traveling thousands of miles through the ocean, they can find their way back by following these magnetic signposts. European eels have an even more remarkable migration. They're born in the Sargasso Sea, a region of the North Atlantic defined not by land boundaries, but by circling currents. The eel larvae drift on ocean currents for months or even years, eventually reaching the coasts of Europe and North Africa. They transform into glass eels, transparent juveniles that swim up rivers and into lakes. The eels spend most of their lives in fresh water, sometimes for decades. Then, when they reach sexual maturity, something triggers a transformation. They develop larger eyes, their skin turns silvery, and they begin the journey back to the Sargasso Sea, thousands of miles across the open ocean, to a place they've never been since they were tiny larvae. They spawn there and die, completing the cycle. But here's the mystery. We've never observed European eels spawning in the Sargasso Sea. We know they go there because that's where we find the larvae. But despite numerous expeditions, nobody has ever witnessed adult eels spawning. It's one of the greatest unsolved mysteries in marine biology. Where exactly do they spawn? At what depth? During what time of year? These seem like simple questions, but the ocean keeps the answers hidden. And it's not just eels and salmon. Bluefin tuna migrate across entire ocean basins, swimming from the western Atlantic to the Mediterranean and back. Some individuals travel over 5,000 miles in a year. They can maintain high speeds for long periods, covering over 100 miles per day. And they do this while maintaining their body temperature significantly above the surrounding water. Bluefin tuna are endothermic, meaning they can generate and retain body heat. This allows them to hunt in cold water where their prey would be sluggish. But maintaining a warm body temperature in cold water requires enormous amounts of energy. Bluefin tuna need to consume massive amounts of food, up to 10% of their body weight each day. The migration routes of bluefin tuna were only recently discovered using satellite tags. Before that, we had no idea these fish crossed entire oceans. We thought different populations stayed in different regions. But the tags revealed something astonishing. Bluefin tuna regularly cross the Atlantic, navigating with precision across thousands of miles of featureless ocean. How do they navigate? Like salmon, they appear to use magnetic fields, sun position, and possibly even the patterns of polarized light in the water. But the exact mechanisms remain unclear. Fish brains are small, yet they're capable of processing complex navigational information and creating mental maps of the ocean. It makes you wonder what else is happening in those small brains. What level of consciousness do fish have? Are they aware of their environment in ways we don't recognize? Recent research suggests fish are far more intelligent than we've given them credit for. Some fish species have been observed using tools. Russes in the Great Barrier Reef will pick up clams in their mouths, swim to a specific rock they've used before, and smash the clam against the rock to break it open. They remember where their anvil rocks are located and return to them repeatedly. That's tool use, memory, and planning, all behaviors once thought to be unique to mammals and birds. Other fish have been shown to recognize individual humans. Archerfish, which hunt by shooting jets of water at insects above the surface, can be trained to recognize human faces, even when the faces are presented at different angles or in black and white. They're processing complex visual information and forming memories. Cleaner fish have been observed exhibiting behavior that looks remarkably like deception. These fish feed on parasites that they pick off larger fish. But sometimes, instead of eating parasites, they'll take a quick bite of the larger fish's healthy tissue, which is more nutritious. The larger fish doesn't like this and will chase the cleaner away. Researchers have observed cleaner fish engaging in reconciliation behavior after taking a forbidden bite. They'll swim back and perform exaggerated cleaning motions as if apologizing to convince the larger fish to let them continue. Is this true deception and reconciliation? Or are we anthropomorphizing, reading too much into simple behavioral patterns? The debate continues, but the more we study fish, the more complex their behavior appears. The ocean is full of intelligence, from the obvious smarts of dolphins and whales to the surprising cognitive abilities of fish and even invertebrates. Octopuses are probably the most famous example of invertebrate intelligence. These 8-armed mollusks have been observed escaping from aquarium tanks, solving puzzles, and even recognizing individual humans. Octopuses have distributed intelligence, with neurons throughout their arms, not just in their central brain. Each arm can act semi-independently, exploring and manipulating objects, while the central brain focuses on other tasks. It's a completely different architecture of intelligence than what we see in vertebrates. And octopuses can change their skin color and texture in milliseconds, creating elaborate camouflage or communication displays. They have specialized cells called chromatophores that contain different pigments. By expanding or contracting these cells, they can create complex patterns across their bodies. Underneath the chromatophores are iridophores, which reflect light to create shimmering metallic effects. And beneath those are leucophores, white cells that reflect ambient light. The result is an animal that can transform its appearance completely in the blink of an eye. An octopus can match the color and texture of rocks, coral, sand, or seaweed with stunning accuracy. Some species can even create false eye spots or mimic other animals. The mimic octopus found in Indonesian waters has been observed imitating lionfish, sea snakes, and jellyfish, depending on what predator it's trying to deter. But here's what's truly mysterious. Octopuses are colorblind. Their eyes contain only one type of light receptor, meaning they see the world in shades of gray, yet they can match colors perfectly. How? Recent research suggests octopuses might see with their skin. Their skin contains proteins similar to those in their eyes, proteins that react to light. The octopus's skin might be detecting color directly, allowing the animal to adjust its appearance without needing to process visual information through its brain. It's sensing and responding to light at the level of individual skin cells. If that's true, it represents a completely novel way of perceiving the environment. The octopus isn't seeing in the traditional sense, it's sensing light across its entire body surface. It's like having millions of tiny eyes all over your skin. The intelligence and sensory capabilities of ocean creatures continue to surprise us. And the more we learn, the more we realize how little we understand about consciousness and cognition in non-human animals. Let's talk about something that connects to this animal communication in the ocean. We know whales and dolphins communicate with complex vocalizations. Humpback whale songs can last for hours and are repeated with variations over time. The songs change from year to year, with new elements being added and old ones dropped, and all the males in a population sing variations of the same song, suggesting they're learning from each other. But what do the songs mean? Are they simply mating displays, like bird songs? Or do they convey specific information about location, food sources, or dangers? We don't know. We can record the songs, analyze their structure, note how they change over time, but we can't translate them. We don't know what the whales are saying to each other, dolphins are even more mysterious. They produce clicks for echolocation and whistles for communication. Each dolphin has a signature whistle, a unique sound pattern that functions like a name. Dolphins will call to each other using these signature whistles, and other dolphins respond. It's the only known example in the animal kingdom, besides humans, of animals using learned sounds to label individuals. But dolphin communication goes far beyond signature whistles. They produce a wide variety of clicks, whistles, and burst pulse sounds. Some researchers believe dolphins might be using these sounds to create acoustic images using echolocation clicks, not just to detect objects, but to communicate detailed information about them. Imagine being able to describe what something looks like by making sounds that echo off it in a specific way. The listener could recreate a mental image from the echo pattern. It would be a completely different form of communication than anything we use. And if dolphins are doing this, we wouldn't even recognize it as language because it doesn't work like our language. There have been numerous attempts to decode dolphin communication over the years. Researchers have used artificial intelligence to analyze thousands of hours of dolphin vocalizations, looking for patterns and structure, and they've found something intriguing. Dolphin vocalizations have statistical properties similar to human language. They have hierarchical structure, with small units combining into larger units in rule-governed ways. But finding structure isn't the same as understanding meaning. We can analyze the syntax without understanding the semantics. It's like listening to someone speak a completely foreign language. You can tell they're communicating, but you have no idea what they're saying. Some researchers have tried to create artificial languages to communicate with dolphins. They've taught dolphins to understand gestural commands and visual symbols. Dolphins can learn dozens of symbols and understand simple sentences. They can even understand the difference between bring the ball to the hoop and bring the hoop to the ball, demonstrating comprehension of word order and grammar. But this is teaching dolphins our language, not learning theirs. And there's a fundamental asymmetry. We're testing whether dolphins can understand us, not whether we can understand them. What would it take to truly decode dolphin communication? We'd need massive amounts of data, recordings of dolphins in natural settings, where we could correlate their vocalizations with their behaviors and context. We'd need artificial intelligence sophisticated enough to find patterns in data that doesn't conform to our expectations of what language looks like. And we'd need to be open to the possibility that dolphin communication might work in ways we haven't imagined. The same challenges apply to other intelligent ocean animals. Sperm whales produce complex click patterns called codas. Different populations of sperm whales have different coda repertoires, like dialects. And individual whales seem to have specific codas they use regularly, possibly serving as identifiers. But beyond that, we don't know what information the codas convey. Are they simply social calls, maintaining group cohesion, or are they exchanging detailed information about feeding locations, dangers, or other topics we can't imagine? The ocean is full of conversations we can't understand. It's humbling to realize that there might be rich, complex communication happening all around us in the ocean, and we're essentially deaf to it. We can hear that animals are vocalizing, but we can't comprehend what they're saying. Now let's shift to talking about something that sounds like it belongs in science fiction: bioluminescent communication. We've discussed bioluminescence as a defensive mechanism or hunting tool, but many organisms also use bioluminescence to communicate with each other. Firefly squid gather in huge numbers during spawning season in Toyama Bay, Japan. The spectacle is so impressive that it's a tourist attraction, People take boat tours to see the glowing squid. The squid have photophores all over their bodies, and they can control the intensity and pattern of their glow. During spawning, they create coordinated light displays, flashing and pulsing in patterns that ripple through the group. What information are they exchanging? Are the displays helping males and females find each other? Are they coordinating group movements? Are they deterring predators by creating a confusing light show? Or is something else happening that we don't understand? Dinoflagellates, the single-celled organisms that create bioluminescent bays, also flash in response to disturbance. But recent research suggests they might be using these flashes to communicate with each other. When one dinoflagellate is disturbed and flashes, nearby dinoflagellates will flash in response. The flashes propagate through the water like a wave. Is this communication in any meaningful sense? Or is it just a mechanical response, each organism reacting independently to the same stimulus? The distinction might seem trivial, but it's philosophically important. If the organisms are truly responding to each other's signals, that implies a level of social interaction we wouldn't expect from single-celled organisms. Deep-sea creatures use bioluminescence in ways we're only beginning to document. Some fish have elaborate photophore patterns that might serve as species recognition signals. In the darkness of the deep ocean, visual recognition is difficult, but a specific pattern of lights could function like a visual signature, allowing members of the same species to find each other. Other creatures appear to use bioluminescence for more complex interactions. The Hawaiian bobtail squid, which we've mentioned, has a sophisticated relationship with its bioluminescent bacteria. The squid can control the intensity of light produced by adjusting blood flow to the light organ, and it can direct the light using reflectors and filters in the organ. But interestingly, the squid also seems to vent its light organ each morning, expelling most of the bacteria. The remaining bacteria multiply during the day, reaching full population by evening. Why does the squid do this? One theory is that it's maintaining quality control, preventing mutant bacteria that don't produce light from taking over the population. The relationship between the squid and its bacteria is so specific that baby squid are born without any bacteria. They must acquire the right species of bacteria from the environment shortly after hatching. The squid's light organ has evolved special structures to attract and house these specific bacteria, while excluding all other microbes. It's a remarkable example of coevolution, two very different organisms evolving together in an intimate partnership. And it's happening all over the ocean, between countless species and their symbiotic partners. Let's talk about symbiosis more broadly, because the ocean is full of these partnerships. Coral reefs themselves are built on symbiosis. Coral polyps are animals, but they host photosynthetic algae called zooxanthellae in their tissues. The algae produce sugars through photosynthesis, which feed the coral. In return, the coral provides the algae with nutrients and a protected environment. This partnership is so important that without it, coral reefs couldn't exist. The zooxanthellae supercharge the coral's energy budget, allowing rapid growth and the construction of massive reef structures. But the partnership is fragile, sensitive to temperature, light, and water chemistry. When conditions become stressful, corals expel their zooxanthellae. This is coral bleaching, the phenomenon that's devastating reefs worldwide. Without their algae, the corals appear white because you can see through their transparent tissue to their white limestone skeletons. And without the food provided by the algae, the corals begin to starve. If conditions return to normal quickly, corals can reacquire zooxanthellae and recover. But if the stress persists, they die. And we're seeing more frequent and severe bleaching events as ocean temperatures rise. The symbiosis between corals and zooxanthellae evolved millions of years ago. It's been refined and optimized over countless generations. But now, climate change is happening so fast that the partnership can't adapt. The system that has worked for millions of years is breaking down in just a few decades. Other symbiotic relationships in the ocean are equally fascinating and vulnerable. Giant clams, which can grow over 4 feet long and weigh over 500 pounds, also host zooxanthellae. The clams have modified their tissues to create translucent windows that allow sunlight to reach the algae living inside. The clams essentially farm the algae, harvesting the sugars they produce. Cleaner fish and their clients engage in a different kind of symbiosis. Cleaner wrasses set up cleaning stations on coral reefs, where larger fish come to have parasites removed. The larger fish benefit from parasite removal, and the cleaner fish get a meal. But the relationship is based on trust. The larger fish could easily eat the cleaner, but they don't. And the cleaner fish have to resist the temptation to cheat by biting healthy tissue instead of just eating parasites. Natural selection has favored cleaner fish that resist this temptation because fish that cheat get ejected from cleaning stations and lose access to food. Some cleaning stations are used by dozens of fish species. The cleaners have to adjust their behavior for different clients. Some fish are more aggressive and will chase away cheating cleaners, while others are more tolerant. The cleaners learn these individual differences and behave accordingly. It's a complex social system requiring memory, individual recognition, and behavioral flexibility, all happening on coral reefs, in interactions that most people never witness or even know about. The ocean is full of these hidden relationships, partnerships, and competitions that structure ecosystems in ways we're only beginning to understand. Now let's talk about something that seems simple but is actually profoundly important: oxygen. The ocean produces more than half of the oxygen in Earth's atmosphere. Not forests, not grasslands, the ocean. Specifically, marine phytoplankton produce the oxygen through photosynthesis. These microscopic organisms floating in the sunlit surface waters are collectively responsible for every second breath you take. Without them, atmospheric oxygen levels would drop dramatically. Complex life on land, including humans, would struggle to survive. But phytoplankton populations are changing as the ocean warms and chemistry shifts. In some regions, populations are declining. In others, they're increasing. The patterns are complex and not fully understood. What we do know is that any significant decrease in phytoplankton productivity would have cascading effects. Less oxygen production, less carbon dioxide absorption, and less food for the marine food web. Everything from zooplankton to whales depends directly or indirectly on phytoplankton. And phytoplankton themselves are surprisingly diverse. There are thousands of species, each adapted to specific conditions of temperature, nutrient availability, and light. Some produce toxins that can cause harmful algal blooms. Others produce chemicals that affect cloud formation and potentially influence climate. Coccolithophores, for example, are phytoplankton covered in calcium carbonate plates. When they bloom, they turn the ocean milky white, visible from space. When they die, their plates sink and accumulate on the ocean floor, forming sediments that eventually become chalk and limestone. The white cliffs of Dover in England are made of ancient coccolithophore plates. Diatoms are another major group of phytoplankton. They have glass shells made of silica in an incredible variety of shapes and patterns. Under a microscope, diatoms look like intricately designed art pieces. When they die, their glass shells accumulate as sediment called diatomaceous earth, which has various industrial uses. But beyond their practical importance, phytoplankton are a reminder of how the smallest organisms can have the largest impacts. These microscopic cells, invisible to the naked eye, collectively weigh more than all the humans on Earth. They process more carbon than all terrestrial plants combined. They're the foundation of the ocean food web and a critical component of the global climate system, and we're changing their environment faster than at any time in millions of years. How will they respond? Will some species decline while others increase? Will overall productivity remain stable, increase, or decrease? These questions have profound implications for the future of life on Earth. Let's talk about another group of small organisms that have huge impacts: viruses. The ocean contains approximately 10 million viruses in every milliliter of water. That's 10 viruses for every bacterium. The total number of viruses in the ocean is incomprehensibly large, probably more than 10 to the 30th power. That's more viruses in the ocean than stars in the universe. Think about that for a moment. The ocean is teeming with viruses, far more than any other biological entity. What are all these viruses doing? They're infecting bacteria, phytoplankton, and other microorganisms. When a virus infects a cell, it hijacks the cell's machinery to produce more viruses. Eventually, the cell bursts, releasing hundreds or thousands of new viruses into the water. This process, called lysis, kills an enormous number of microorganisms every day. Perhaps 20% to 40% of all bacteria in the ocean are killed by viruses daily. That might sound bad, but it's actually crucial for ecosystem function. When cells are lysed, their contents are released into the water. Nutrients and organic molecules that were locked up in living cells become available to other organisms. This viral shunt, as it's called, recycles nutrients and keeps them in the surface layer where phytoplankton can use them. Viruses also affect which species dominate in the ocean. When one species becomes very abundant, viruses that infect that species multiply and start killing it off. This prevents any single species from dominating, maintaining diversity, and viruses transfer genes between organisms. When a virus infects a cell, it sometimes incorporates pieces of the host's DNA into its own genome. When that virus infects a different cell, it can transfer those genes. This horizontal gene transfer accelerates evolution and spreads beneficial genes through microbial populations. Some of the most important genes in marine bacteria were probably acquired through viral transfer. Genes for photosynthesis, nutrient metabolism, and other key functions have been found in viral genomes. Viruses aren't just killing machines, they're genetic engineers, reshaping the microbial community through gene transfer. The ocean's viral community is incredibly diverse. Most viruses have never been cultured or studied in detail. We know they exist only through genetic sequencing of ocean water samples, and we're discovering that many viruses are specific to their hosts, infecting only one or a few closely related species. This specificity means that viruses can regulate specific populations without affecting the entire microbial community. It's precise ecological control at the microscopic level, but we're only beginning to understand the ocean's virome. New sequencing technologies are revealing viral diversity we never suspected, and we're finding viruses in unexpected places, infecting organisms we didn't know were susceptible to viral infection. The ocean's viral ecology is an entire field of study that barely existed 30 years ago. Now we realize that viruses are fundamental to how ocean ecosystems function. They're not just pathogens, they're integral components of the system. Let's shift to talking about something mysterious and ancient, ocean fossils, and what they tell us about the past. The ocean floor contains a remarkable record of Earth's history. Sediments accumulate slowly, layer upon layer, preserving the remains of organisms and chemical signatures of past conditions. By drilling cores from the ocean floor and analyzing the layers, scientists can reconstruct past climates, ocean circulation patterns, and the evolution of marine life. Some of these cores extend back millions of years, providing a continuous record of environmental change. What they've revealed is fascinating and sometimes disturbing. Earth's climate has varied dramatically over geological time. There have been periods when the poles had no ice, and the ocean was much warmer than today. There have been other periods when ice extended far from the poles and sea levels were hundreds of feet lower. These changes happened slowly, typically over thousands or millions of years. Marine life had time to adapt, migrating to new areas or evolving new adaptations. But the current rate of change is unprecedented in the geological record. We're warming the ocean faster than at any time in the past 66 million years, since the asteroid impact that killed the dinosaurs. Marine organisms haven't experienced this rate of change in their evolutionary history. Many won't be able to adapt fast enough. The fossil record also shows us that ocean life has changed dramatically over Earth's history. The earliest life forms were marine microorganisms, appearing over 3.5 billion years ago. For most of Earth's history, life was entirely oceanic and entirely microscopic. Complex multicellular life didn't appear until about 600 million years ago. Then, in a geological blink of an eye called the Cambrian explosion, marine life diversified dramatically. Most major animal groups appeared during this period, including the ancestors of everything from worms to vertebrates. What caused the Cambrian explosion? Scientists debate this question, but the leading theories involve increasing oxygen levels and the evolution of predation. As oxygen accumulated in the atmosphere and ocean, it became possible for animals to grow larger and more active. And once some animals started eating other animals, an evolutionary arms race began. Prey evolved armor and defensive strategies. Predators evolved better weapons and hunting techniques. The result was an explosion of diversity and innovation. The ocean has witnessed several mass extinctions since then. The Permian-Triassic extinction, about 252 million years ago, was the worst. It's estimated that 96% of marine species went extinct. The cause was probably massive volcanic eruptions that released enormous amounts of carbon dioxide and sulfur dioxide into the atmosphere. The ocean became acidic, oxygen levels dropped, and temperatures soared. It took millions of years for ecosystems to recover. The Cretaceous-Paleogene extinction, 66 million years ago, was caused by an asteroid impact. The impact created massive tsunamis, ejected enough debris into the atmosphere to block sunlight for years, and caused global wildfires. Marine ecosystems collapsed. Ammonites, which had been abundant for hundreds of millions of years, went extinct. Marine reptiles like mosasaurs and plesiosaurs disappeared. But some groups survived and eventually thrived in the post-extinction world. Modern bony fish, sharks, and marine mammals all trace their origins to survivors of these ancient catastrophes. The fossil record shows us that life is resilient over geological timescales. After each mass extinction, life recovered and diversified again. But recovery took millions of years. And for the species that went extinct, there was no recovery. They were gone forever. We're now in the midst of what many scientists call the sixth mass extinction. Species are disappearing at rates comparable to past mass extinctions, but this time the cause is human activity. Habitat destruction, overfishing, pollution, and climate change are all contributing. The question is whether this extinction will follow the pattern of previous ones. Will life eventually recover and diversify again? Probably, but it will take millions of years, and humans might not be around to see it. The fossil record also contains mysteries that we haven't fully solved. There are periods in Earth's history when conditions were very different from today, and we're not entirely sure why. The Cryogenian period, about 700 million years ago, saw the most extreme ice age in Earth's history. Evidence suggests the entire planet was covered in ice, even at the equator. It's called Snowball Earth, and it lasted for millions of years. How did life survive Snowball Earth? The ocean was frozen, at least on the surface, but there must have been liquid water below the ice, and possibly around volcanic vents. Life persisted, though probably in very limited refuges. Eventually, volcanic activity released enough carbon dioxide to create a super greenhouse effect, melting the ice. The planet thawed, and life expanded again. But the details of how this happened, and exactly what triggered the initial freezing and the eventual thawing, remain debated. The ocean's fossil record is full of these mysteries, periods, and events that challenge our understanding of how Earth's systems work. Let's talk about something more recent, but equally mysterious: ocean dead zones. These are areas where oxygen concentrations have dropped so low that most marine life cannot survive. Dead zones are expanding around the world, driven by nutrient pollution and warming waters. When excess nutrients from agricultural runoff and sewage enter the ocean, they fuel massive algal blooms. The algae grow rapidly, then die en masse. As they decompose, bacteria consume oxygen from the water. If oxygen consumption exceeds oxygen supply through mixing and photosynthesis, oxygen levels crash. The result is an area where fish, crustaceans, and most other mobile organisms either flee or die. Only organisms that can tolerate very low oxygen, like certain bacteria and primitive worms, can survive. The Gulf of Mexico has one of the largest dead zones in the world. Every summer, a hypoxic zone forms where the Mississippi River delivers nutrient-rich water to the Gulf. The zone can cover over 8,000 square miles, an area roughly the size of New Jersey. This affects fisheries, tourism, and coastal communities. Fish and shrimp populations decline, forcing commercial and recreational fishers to go elsewhere. The economic impact runs into hundreds of millions of dollars annually, and the Gulf of Mexico dead zone is just one of over 400 documented dead zones worldwide. They're appearing in coastal waters on every continent. Some are seasonal, forming in summer and dissipating in winter when water mixes more. Others are permanent, lasting year-round. The Baltic Sea has areas that have been oxygen depleted for decades. The Black Sea has a massive anoxic zone in its deep waters. Lakes and enclosed seas are particularly vulnerable because water circulation is limited. Climate change is making the problem worse. Warmer water holds less dissolved oxygen, and warming strengthens stratification, reducing vertical mixing that brings oxygen to deep waters. So even without increasing nutrient pollution, dead zones would likely expand as the ocean warms. But we can reduce dead zones by controlling nutrient pollution, better agricultural practices, improved sewage treatment, and restoration of wetlands that filter nutrients can all help. Some areas that have implemented strict nutrient controls have seen dead zones shrink. It's possible to reverse the trend, but it requires commitment and investment. The ocean's dead zones are a warning sign. They show us what happens when we push ecosystems beyond their limits. They're areas where the ocean has stopped functioning properly, where the intricate balance of life and chemistry has collapsed into lifelessness. And if we're not careful, dead zones could expand to cover much larger areas. Now let's talk about something that connects many of the themes we've discussed, the ocean's microbiome. Just as humans have a microbiome, communities of microorganisms living in and on our bodies, the ocean has its own microbiome. Bacteria, archaea, protists, viruses, and fungi, all living in the water and on surfaces. This ocean microbiome is vastly more diverse and important than the human microbiome. Marine microbes process nutrients, produce oxygen, consume organic matter, and mediate chemical reactions that are crucial for life on Earth. And like the human microbiome, the ocean microbiome is sensitive to disturbances, pollution, warming, acidification, and other stresses can shift microbial communities, causing some species to decline and others to proliferate. These shifts can have cascading effects through the ecosystem. If bacteria that fix nitrogen decline, phytoplankton might be nutrient limited. If bacteria that decompose organic matter become less efficient, nutrients might not be recycled quickly enough. If harmful bacteria proliferate, they might produce toxins that affect other organisms. We're only beginning to understand the ocean's microbiome and how human activities are affecting it. Advanced genetic sequencing allows us to identify microbes without culturing them in the lab. This has revealed that ocean microbial diversity is far greater than anyone suspected. There might be tens of thousands or even hundreds of thousands of microbial species in the ocean. Most have never been studied, most have no names, and for most we have no idea what they do or what role they play in the ecosystem. It's humbling to realize that the most abundant and arguably most important organisms in the ocean are invisible to us without microscopes, and that we know almost nothing about the vast majority of them. The ocean's microbiome is another frontier of scientific exploration. Every sample of ocean water contains species new to science. Every deep-sea vent system hosts unique microbial communities. Every drop of seawater is a universe of microscopic life. Let's end this extended journey through ocean mysteries by talking about the future. What will the ocean look like in 50 years? In 100 years? In 1,000 years? If we continue on our current path, the changes will be profound and largely negative. Ocean temperatures will continue to rise, coral reefs will largely disappear, fish populations will decline further, and acidification will increase. Dead zones will expand, ice will continue to melt, and sea levels will rise significantly. Many coastal cities will face regular flooding. Some small island nations will become uninhabitable. The economic and human costs will be staggering. But this future is not inevitable. We have the knowledge and technology to change course. We can reduce carbon emissions, protect marine habitats, manage fisheries sustainably, and reduce pollution. Some countries and communities are already doing this. Marine protected areas are expanding. Some fish populations are recovering where they're managed well. Renewable energy is becoming cheaper and more widespread. The question is whether we'll act quickly enough and at a large enough scale. The ocean is resilient, but it has limits. Some changes we've already set in motion will continue for decades or centuries, even if we stop all harmful activities today. But we can still avoid the worst outcomes. We can still preserve much of the ocean's biodiversity and ecological function. We can still have productive fisheries and healthy coastal ecosystems. It requires making the ocean a priority. It requires recognizing that ocean health is inseparable from human well-being. It requires understanding that we are not separate from the ocean, but part of it. Every breath you take connects you to the ocean. Every drop of rain that falls comes from the ocean. The stability of our climate depends on the ocean. The food for billions of people comes from the ocean. We are ocean beings, living on an ocean planet, and the ocean's future is our future. As you drift into sleep, let these mysteries wash over you like waves. Think about the creatures in the crushing depths, adapted to conditions we can barely imagine. Think about the songs of whales carrying across thousands of miles of water. Think about the bioluminescent displays in the darkness, light shows that no human will ever witness. Think about the microscopic phytoplankton producing the oxygen you breathe. Think about the currents circulating heat and nutrients around the globe. Think about all the species we haven't discovered, all the secrets the ocean still holds. The ocean is vast, ancient, powerful, and mysterious. It's been here for billions of years and will be here long after we're gone. But while we're here, we have the privilege and responsibility to explore it, understand it, and protect it. The ocean doesn't need us, but we desperately need the ocean. So dream of the deep tonight. Dream of the mysteries waiting to be discovered. Dream of the creatures we've never seen and the places we've never been. Dream of an ocean that's healthy and thriving, full of life and wonder. And when you wake, remember that the ocean's story is still being written, and we all have a part to play in how it unfolds. Sleep well. May your dreams be as deep as the ocean, and may you wake with wonder in your heart and determination in your mind. The ocean is calling. It always has been. The question is whether we're finally ready to listen. Good night. Retry. I continue writing after the question is whether we're finally ready to listen. Mark down. The question is whether we're finally ready to listen. Because the ocean has been trying to tell us things for a very long time. It's been showing us the consequences of our actions through dying coral reefs and collapsing fish populations. It's been warning us with rising temperatures and changing chemistry. It's been revealing its secrets slowly through every expedition and every discovery. But we haven't always been paying attention. We've treated the ocean as infinite, as unchangeable, as something that exists for our benefit alone. We've taken from it without thinking about the cost. We've dumped our waste into it, assuming it would simply disappear. The question is whether we're finally ready to listen. Because the ocean has been trying to tell us things for a very long time. It's been showing us the consequences of our actions through dying coral reefs and collapsing fish populations. It's been warning us with rising temperatures and changing chemistry. It's been revealing its secrets slowly through every expedition and every discovery. But we haven't always been paying attention. We've treated the ocean as infinite, as unchangeable, as something that exists for our benefit alone. We've taken from it without thinking about the cost. We've dumped our waste into it, assuming it would simply disappear. We've harvested its creatures without considering whether they could sustain the pressure. And now the ocean is responding, not with anger or vengeance, but with change. Changes that will affect every living thing on this planet. Let's talk about something we haven't fully explored yet. The ocean's memory. The ocean remembers everything that happens to it. Not in a conscious way, of course, but through physical and chemical traces that persist for years, decades, centuries, or even millennia. When a nuclear weapon is detonated, it releases radioactive isotopes into the environment. These isotopes have distinct signatures that can be detected decades later. Scientists have used these signatures to trace ocean currents and mixing patterns. Water that was at the surface during the atmospheric nuclear tests of the 1950s and 1960s absorbed these isotopes. As that water sank and circulated through the deep ocean, it carried the isotopes with it. By measuring the concentration and distribution of these isotopes, oceanographers can map how water moves through the ocean. They can calculate how long it takes for surface water to reach the deep ocean. They can identify different water masses and track their origins. The ocean remembers the nuclear age, and that memory helps us understand ocean circulation. The ocean also remembers past climates through the shells of tiny organisms. Foraminifera are single-celled organisms that build calcium carbonate shells. When they die, their shells sink to the ocean floor and are preserved in sediment. The chemistry of these shells reflects the water temperature and chemistry when the organism was alive. By drilling cores from the ocean floor and analyzing forum shells at different depths, scientists can reconstruct past ocean temperatures going back millions of years. They can see when the ocean was warmer or cooler, when ice ages came and went. The forum shells are like tiny time capsules, each one preserving a snapshot of ocean conditions from the distant past. Ice cores from Antarctica and Greenland also preserve ocean memories. Snow that falls on ice sheets contains tiny bubbles of ancient air. By drilling deep into the ice and analyzing these bubbles, scientists can measure atmospheric carbon dioxide and methane concentrations going back 800,000 years. And because the ocean and atmosphere exchange gases, changes in atmospheric composition reflect changes in the ocean. What these ice cores reveal is sobering. For the past 800,000 years, atmospheric carbon dioxide has cycled between about 180 parts per million during ice ages and 280 parts per million during warm periods. It's never gone above 300 parts per million in that entire time span. Until now, current atmospheric carbon dioxide is over 420 parts per million and rising. We've pushed it far beyond anything the planet has experienced in hundreds of thousands of years, and the ocean is absorbing about 30% of that excess carbon dioxide, changing its chemistry in the process. The ocean remembers this too, through its changing pH, through its warming temperatures, through the species that thrive and the species that disappear. Future scientists will be able to look at ocean sediments from our era and see exactly what we did. They'll see the chemical signatures of fossil fuel burning, the plastic particles embedded in sediment layers, the changes in forum shell chemistry that indicate rapid warming. Our impact on the ocean will be visible in the geological record for millions of years. We're creating a distinct layer in Earth's stratigraphy, a boundary that marks when humans became a planetary scale force. Some scientists call this the Anthropocene, the age of humans, and the ocean is recording it all. But the ocean's memory isn't just a historical record, it also affects the ocean's future. Heat that the ocean absorbs today will continue to affect ocean circulation and climate for decades or centuries. Carbon dioxide that dissolves into the ocean today will continue to acidify the water for hundreds of years. Plastic that enters the ocean today will persist for centuries or millennia. The ocean has long-term memory, and our actions today will have consequences that extend far into the future. This is both sobering and empowering. Sobering because we can't undo the changes we've already caused, at least not quickly. But empowering because the actions we take today will also have long-term effects. If we reduce carbon emissions now, the ocean will eventually absorb less carbon dioxide and begin to recover from acidification. If we establish marine protected areas now, fish populations will rebuild and ecosystems will recover. If we reduce plastic pollution now, less plastic will accumulate in ocean sediments and food webs. The ocean's memory works both ways, recording both our harms and our efforts to heal. Let's talk about something that connects the ocean's past to its future: sea level rise in much more detail. We've mentioned that sea levels are rising due to thermal expansion and melting ice. But the story is more complex and more ominous than those simple facts suggest. Sea level has changed dramatically throughout Earth's history. During the last ice age, about 20,000 years ago, sea level was roughly 400 feet lower than today. So much water was locked up in ice sheets that vast areas of continental shelf were exposed. You could walk from Asia to North America across what's now the Bering Strait. The British Isles were connected to continental Europe. Many of today's coastal cities would have been located far inland. As the ice melted and the climate warmed, sea level rose rapidly. Between 20,000 and 8,000 years ago, sea level rose about 400 feet, an average of about 3 feet per century. But the rise wasn't smooth or steady. There were periods of very rapid rise, sometimes over 10 feet per century, punctuated by slower periods. These rapid rises were probably caused by the collapse of ice sheets. When an ice sheet becomes unstable, it doesn't melt gradually. It can collapse suddenly, dumping enormous amounts of ice into the ocean in just a few decades or centuries. This causes rapid sea level rise that coastlines can't adjust to. Evidence from coastal sediments shows that some ancient human settlements were inundated by rising seas. Stories of great floods appear in the mythology of many cultures around the world. While most of these stories are probably mythological, some might preserve memories of actual flooding events as sea levels rose after the Ice Age. For the past few thousand years, sea level has been relatively stable, rising only slowly. This stability allowed human civilizations to develop along coastlines, building cities and infrastructure, with the assumption that sea level wouldn't change significantly. But that assumption is no longer valid. Sea level began rising more rapidly in the late 19th century as global temperatures increased. The rate has accelerated since then. Currently, sea level is rising about 3.3 millimeters per year globally, though the rate varies by location. That might not sound like much, but it compounds over time, and the rate is accelerating. Satellite measurements show that the rate of sea level rise is increasing by about 0.08 millimeters per year each year. This acceleration is driven by two factors. The ocean is warming faster, causing more thermal expansion, and ice sheets are losing mass at increasing rates. The Greenland ice sheet is now losing about 280 billion tons of ice per year. The Antarctic ice sheet is losing about 150 billion tons per year. These numbers are staggering, and they're increasing. If all the ice in Greenland melted, sea level would rise about 24 feet globally. If all the ice in Antarctica melted, sea level would rise about 200 feet. Obviously, this won't happen overnight. These ice sheets took hundreds of thousands of years to form. But we don't need complete melting to cause catastrophic impacts. Even a few feet of sea level rise will have enormous consequences. Many of the world's largest cities are located on coastlines at low elevations. New York, Miami, New Orleans, Houston, Shanghai, Mumbai, Bangkok, Jakarta, Lagos, and dozens of others. A rise of just 3 feet would put much of Miami underwater during high tides. Storm surges would reach much farther inland, flooding areas that are currently safe. And it's not just major cities. Small island nations are on the front lines of sea level rise. The Maldives, with an average elevation of just 5 feet above sea level, faces an existential threat. Tuvalu, Kiribati, and the Marshall Islands are in similar situations. As sea level rises, these nations will lose land area, their fresh water supplies will be contaminated by salt water, and eventually they may become uninhabitable. Where will the people go? Climate migration is already happening, and it will increase as sea levels rise. Tens of millions of people will be displaced from coastal areas over the coming decades. This will create humanitarian crises, political tensions, and economic disruptions. The economic costs of sea level rise are difficult to calculate, but will certainly run into trillions of dollars. Coastal infrastructure will need to be relocated or protected with seawalls and other barriers. Some areas will have to be abandoned entirely. Property values in vulnerable areas will collapse. Insurance companies are already refusing to cover properties in high-risk coastal zones. And sea level rise doesn't affect all coastlines equally. Ocean currents, gravitational effects from ice sheets, and land subsidence all influence local sea level. Some areas are experiencing sea level rise much faster than the global average. The US Gulf Coast and East Coast are particularly vulnerable. The Gulf Stream helps to hold down sea level along the East Coast. If the Gulf Stream weakens, as it appears to be doing, sea level along the coast could rise faster than the global average. Land subsidence compounds the problem in many areas. Cities built on river deltas or reclaimed land are sinking as the ground compacts. New Orleans is subsiding in some areas at rates of over an inch per year. Jakarta is sinking so fast that the Indonesian government is planning to relocate the capital. When you combine local subsidence with global sea level rise, some areas face relative sea level rise of several inches per decade. That's fast enough to see significant changes within a human lifetime. Sea level rise also affects coastal ecosystems. Salt marshes and mangrove forests provide crucial habitat for fish and birds, and they protect coastlines from erosion and storm surge. But these ecosystems need to migrate inland as sea level rises. If development blocks their migration path, they'll be squeezed between rising seas and human infrastructure. Many coastal wetlands are already being lost to this coastal squeeze. Coral reefs are also threatened by sea level rise, though in a more complex way. Reefs can grow vertically as sea level rises, but only if they're healthy. Stressed reefs that are suffering from bleaching, disease, or other problems may not be able to keep up with the rapid sea level rise. They'll drown, left in water too deep for them to survive. The future rate of sea level rise is uncertain and depends on how much the planet warms. Conservative estimates suggest sea level will rise 1 to 2 feet by 2100. More aggressive estimates, accounting for possible ice sheet instability, suggest 3 to 6 feet or even more. And sea level will continue rising long after 2100. Even if we stopped emitting greenhouse gases tomorrow, sea level would continue rising for centuries due to the thermal inertia of the ocean and the slow response of ice sheets. We've committed to a certain amount of sea level rise already. It's locked in by the warming that's already occurred. The question is how much additional rise will cause with future emissions, and that's up to us. Let's talk about something we've touched on, but deserves deeper exploration: the ocean's role in weather and climate. We've mentioned hurricanes and El Niño, but the ocean's influence on weather is far more pervasive than these dramatic examples suggest. Every raindrop that falls on land came from the ocean. The sun evaporates water from the ocean surface. The water vapor rises into the atmosphere and eventually condenses into clouds and precipitation. This is the hydrological cycle, and the ocean is its engine. But the ocean doesn't just passively supply water vapor. It actively influences where and when precipitation occurs through its temperature patterns and currents. Warm ocean water evaporates more readily than cold water, so areas with warm sea surface temperatures receive more rainfall. This is why tropical regions are so wet. The warm tropical oceans provide abundant moisture for rain. Ocean currents transport heat from the equator toward the poles, creating temperature gradients that drive atmospheric circulation. These circulation patterns, like the jet streams, guide weather systems and determine where storms form and where they travel. The ocean also moderates temperature extremes on land. Coastal areas have milder climates than inland areas at the same latitude because the ocean absorbs and releases heat slowly. In summer, the ocean stays cooler than land, and winds blowing from ocean to land bring cooler temperatures. In winter, the ocean stays warmer than land, and winds from the ocean moderate cold temperatures. This moderating effect extends hundreds of miles inland in some regions. Western Europe's mild climate, despite its high latitude, is largely due to warm water transported by the Gulf Stream and North Atlantic Drift. Without this oceanic heat transport, London would have a climate more like Winnipeg, Canada, which is at a similar latitude. But climate change is disrupting these patterns. As the ocean warms, evaporation increases, leading to more intense rainfall in some areas. But warming also changes atmospheric circulation patterns, causing droughts in other areas. Some regions are getting wetter, others drier, and the patterns we've relied on for agriculture and water management are shifting. Hurricanes and typhoons derive their energy from warm ocean water. They form over tropical oceans when sea surface temperatures exceed about 26-27 degrees Celsius. The warm water provides the energy that drives the storm's circulation. As ocean temperatures rise, more areas reach the threshold for hurricane formation. The hurricane season is lengthening, starting earlier and ending later. And there's evidence that the strongest storms are becoming more intense. Hurricane intensification happens when a storm moves over very warm water. The warm water provides additional energy, causing wind speeds to increase rapidly. Climate change is creating larger areas of very warm water, allowing storms to intensify more often. Hurricane Harvey in 2017 intensified rapidly before hitting Texas, then stalled over Houston and dumped record rainfall. The storm dropped over 60 inches of rain in some areas, causing catastrophic flooding. Climate scientists calculated that climate change made the rainfall about 15% more intense and increased the probability of such an event by a factor of 3. Hurricane Maria in 2017 devastated Puerto Rico, causing over 3,000 deaths and tens of billions of dollars in damage. The storm intensified to Category 5 over exceptionally warm Atlantic water. These examples show how the ocean's temperature directly affects extreme weather events. And as the ocean continues to warm, we can expect more intense hurricanes, though not necessarily more hurricanes overall. The frequency of hurricanes might stay the same or even decrease slightly, but the proportion of intense Category 4 and 5 storms is likely to increase. The ocean also influences weather through phenomena like the El Niño Southern Oscillation, which we've mentioned. El Niño and its counterpart La Niña are fluctuations in Pacific Ocean temperatures that occur every 2 to 7 years. They have global impacts on weather patterns. During El Niño, warm water spreads across the tropical Pacific, weakening trade winds and changing atmospheric circulation. This causes droughts in some regions, including Australia, Indonesia, and parts of Africa. It causes flooding in others, including Peru, California, and the southern United States. La Niña has opposite effects. with cool water in the tropical Pacific strengthening trade winds and shifting weather patterns in different directions. La Niña tends to bring drought to the southern US and increased rainfall to the Pacific Northwest. Climate change appears to be affecting El Niño and La Niña. Some climate models predict more frequent or more intense El Niño events. Others suggest the patterns might become more irregular and harder to predict. What's clear is that the baseline conditions are changing, with the tropical Pacific generally warming. These changes in ocean temperature patterns will affect weather worldwide. Agricultural systems that have adapted to predictable rainfall patterns will face new challenges. Water resources that depend on seasonal precipitation will become less reliable. The ocean's influence on weather is so pervasive that changes in ocean conditions ripple through every aspect of human society. Let's talk about something fascinating: how ocean creatures have inspired human technology. Biomimicry, the practice of learning from and imitating nature's designs, has a long history in ocean research. Shark skin, for example, has inspired new materials and designs. Shark skin isn't smooth. It's covered in tiny tooth-like scales called dermal denticles. These scales are arranged in overlapping patterns that reduce drag and prevent fouling by parasites and algae. Engineers have created synthetic materials that mimic shark skin texture. These materials reduce drag on ship hulls, improving fuel efficiency. They also resist bacterial growth, making them useful for medical applications in places where hygiene is critical. Swimsuit manufacturers created full-body suits with shark skin-inspired textures. These suits were so effective at reducing drag that they were banned from competitive swimming because they provided an unfair advantage. The boxfish might seem like an unlikely source of inspiration with its rigid box-shaped body, but the boxfish's shape is remarkably efficient. Despite its boxy appearance, it moves through water with minimal drag and excellent stability. Car manufacturers studied the boxfish's shape and aerodynamics when designing more fuel-efficient vehicles. The Mercedes-Benz Bionic car concept was directly inspired by the boxfish, achieving a drag coefficient better than many sports cars despite its boxy shape. Whale flippers have bumps along their leading edges called tubercles. These bumps seemed counterintuitive. You'd think smooth flippers would be more efficient, but research showed that the tubercles actually improve performance. The bumps create vortices that allow the flipper to maintain lift at higher angles of attack. This gives whales better maneuverability and allows them to make tighter turns. Engineers have applied this principle to wind turbine blades, fan blades, and aircraft wings. Blades with leading-edge tubercles are more efficient and quieter than smooth blades. Mussels produce incredibly strong adhesive that works even underwater. This is remarkable because most adhesives don't work when wet. The mussel adhesive contains special proteins that displace water and bond to surfaces. Researchers are developing synthetic adhesives inspired by mussel glue. These could be used in medical applications, like sealing wounds or attaching devices inside the body. They could also be used in marine construction, bonding materials underwater without needing to drain and dry the work area. The mantis shrimp has the most complex color vision of any animal, with 16 types of color receptors compared to humans' 3. It can also see polarized light and even circular polarized light, which almost no other animal can detect. Its eyes inspire the development of new cameras and sensors. Mantis shrimp eyes are also remarkably good at detecting cancer cells. The way polarized light reflects off cancerous tissue is different from healthy tissue, and sensors inspired by mantis shrimp vision could help doctors detect cancer earlier. Perhaps most impressively, mantis shrimp have spring-loaded claws that they can snap shut with incredible force and speed. The strike is so fast that it creates cavitation bubbles in the water. When these bubbles collapse, they produce a shock wave and even a flash of light. Engineers study the mantis shrimp's strike mechanism to develop better shock-absorbing materials and more efficient energy storage systems. The principles could be applied to everything from body armor to mechanical systems that need to deliver sudden bursts of energy. Octopuses inspire robotics research in multiple ways. Their soft, flexible bodies can squeeze through incredibly small openings. They can manipulate objects with precision using their arms, which contain millions of neurons distributed throughout. Soft robotics researchers are creating octopus-inspired robots that can navigate complex environments, manipulate delicate objects, and squeeze through tight spaces. These robots could be used in search and rescue operations, medical procedures, or maintenance of complex machinery. The octopus's camouflage abilities are also inspiring materials research. Creating artificial materials that can change color and texture on demand would have applications in displays, adaptive camouflage, and even architecture. Jellyfish have inspired the design of underwater vehicles. Their pulsing propulsion is efficient and creates minimal disturbance in the water. Robotic jellyfish could be used for ocean monitoring, collecting data while drifting on currents and pulsing to control their position. The ocean has been solving engineering problems for billions of years through evolution. Every creature is a testament to solutions that work, refined through countless generations. We're just beginning to learn from this vast library of natural designs, and there's so much more to discover. For every species we've studied, there are dozens or hundreds we haven't examined in detail. Each one might hold insights that could solve problems we haven't even thought of yet. The ocean is not just a source of food and resources, it's a source of knowledge and inspiration. Let's talk about ocean acidification in even greater depth, because this is one of the most serious and least appreciated threats facing the ocean. When carbon dioxide dissolves in seawater, it doesn't just disappear. It undergoes chemical reactions that change the water's chemistry. Carbon dioxide reacts with water to form carbonic acid. This acid then dissociates, releasing hydrogen ions and lowering the pH. The pH scale is logarithmic, so small changes in pH represent large changes in acidity. The ocean's pH has dropped from about 8.2 before the Industrial Revolution to about 8.1 today. That 0.1 unit decrease represents a 30% increase in acidity, and the ocean is becoming more acidic faster than at any time in the past 300 million years. Marine organisms haven't experienced this rate of change in their evolutionary history. The increased acidity affects calcium carbonate, the compound that many marine organisms use to build shells and skeletons. There are two main forms of calcium carbonate in the ocean, calcite and aragonite. Aragonite is more soluble, meaning it dissolves more easily in acidic conditions. Many organisms use aragonite to build their shells or skeletons, corals, pteropods, some mollusks, some types of plankton. As the ocean becomes more acidic, it becomes harder for these organisms to build and maintain their calcium carbonate structures. In laboratory experiments, pteropods placed in water with projected end-of-century pH showed shell dissolution within 48 hours. Their shells literally started dissolving while they were still alive. Corals also struggle in more acidic water. They can still build skeletons, but the process is slower and requires more energy. This makes corals more vulnerable to other stresses like warming water and disease. But acidification doesn't just affect shell-building organisms. It also affects fish behavior and physiology. Research has shown that fish raised in acidified water have altered sensory systems. Clownfish larvae, for example, lose their ability to detect predators using smell. In normal water, clownfish avoid the smell of predators. In acidified water, they're actually attracted to predator scents. This isn't learnt behavior that can be fixed. It's a disruption of the fish's chemosensory system. The acidification interferes with how neurons process information, essentially scrambling the fish's sense of smell. Other fish species show similar problems. Some lose their ability to distinguish between safe and dangerous habitats. Others become bolder and take more risks, swimming in open water where they're vulnerable to predators. The mechanisms aren't fully understood, but acidification appears to affect the function of GABA receptors in fish brains. GABA is an inhibitory neurotransmitter, and when its function is disrupted, behavior changes in unexpected ways. Squid and octopuses also show behavioral changes in acidified water. Some species become lethargic, moving less and responding more slowly to stimuli. This could make them more vulnerable to predators and less successful at catching prey. The food web effects of acidification are complex and potentially severe. If pteropods decline due to shell dissolution, the fish, seabirds, and whales that eat them will lose a crucial food source. If corals can't maintain their skeletons, reef ecosystems will collapse, affecting thousands of species. If fish behavior is disrupted, population dynamics will change in unpredictable ways. And these changes are happening now, not in some distant future. We can measure the effects of acidification in ocean waters today. The aragonite saturation horizon, the depth below which aragonite dissolves, is rising in many parts of the ocean. Areas that were once saturated with aragonite, where shell building was easy, are becoming undersaturated. In some regions, particularly near the poles where cold water absorbs more carbon dioxide, surface waters are already becoming corrosive to aragonite during certain times of the year. The Pacific Northwest coast of North America has experienced episodes of water so acidic that oyster larvae couldn't survive. Oyster hatcheries had to adapt, carefully monitoring water chemistry and timing their spawning to avoid the most acidic periods. But wild oysters and other shell-building organisms don't have that option. They're experiencing conditions that exceed their tolerances, and populations are declining. Ocean acidification also interacts with other stresses in complex ways. Warm water holds less oxygen, and organisms in warm water have higher metabolic rates, increasing their oxygen needs. Add acidification, which also affects metabolism and respiration, and organisms face a triple threat. In some parts of the ocean, organisms are already living near their physiological limits. They're tolerating water that's warmer, more acidic, and lower in oxygen than their ancestors experienced. Any additional stress could push them over the edge into collapse. The solution to ocean acidification is the same as the solution to climate change: reduce carbon dioxide emissions. There are no quick technological fixes for acidification. We can't feasibly add alkaline chemicals to the ocean to neutralize the acid. The volumes are too vast. The only way to stop acidification is to stop adding carbon dioxide to the atmosphere. And even if we stopped all emissions today, the ocean would remain acidic for decades or centuries before natural processes restore pH to pre-industrial levels. We've already committed to a certain amount of acidification through past emissions. The question is how much more we'll add with future emissions. Let's talk about something that offers a glimmer of hope: ocean recovery. Despite all the damage we've done, the ocean has shown a remarkable ability to recover when given the chance. Marine protected areas, where fishing and other extractive activities are limited or banned, have shown clear benefits. Fish populations inside protected areas grow larger and more abundant. Biodiversity increases as ecosystems recover from overfishing pressure, and the benefits spill over into surrounding areas as fish from the protected zones disperse and support fisheries. The Phoenix Islands protected area in Kiribati is one example. When it was established in 2008, it protected over 150,000 square miles of ocean. Surveys have shown increases in shark and large fish populations, and coral reefs inside the protected area are healthier than those outside. The Papahanaumokuakea Marine National Monument around the northwestern Hawaiian Islands has shown similar results. Since fishing was banned, populations of apex predators like sharks have increased. The protected area serves as a refuge, allowing populations to recover and potentially replenish fished areas elsewhere. Small-scale marine reserves have also demonstrated dramatic recoveries. In the Philippines, coastal communities establish small, no-take zones around their reefs. Within a few years, fish populations inside the reserves increased by 200 to 400%. The spillover effect increased catches in adjacent fishing areas, providing both conservation and economic benefits. These examples show that protection works. When we remove fishing pressure and give ecosystems time to recover, they do. But protection needs to be maintained long-term, and it needs to cover enough area to matter. Some scientists advocate protecting 30% of the ocean by 2030. Currently, only about 7% of the ocean is protected, and much of that protection is weak, allowing some extractive activities. Expanding protection to 30% with strong enforcement could allow significant recovery of ocean ecosystems. Habitat restoration is another promising approach. Coral restoration projects are transplanting nursery-grown corals onto damaged reefs. The survival rates vary, but successful projects have seen corals grow and reproduce, slowly rebuilding reef structure. Oyster reef restoration is happening in many estuaries. Oysters filter water, improve water quality, and create habitat for other species. Restoration projects have reintroduced oysters to areas where they'd been harvested to near extinction. The results have been positive, with improving water quality and recovering fish populations. Mangrove restoration is occurring in tropical regions. Mangroves provide crucial habitat for juvenile fish, protect coastlines from erosion, and sequester carbon. Restored mangrove forests have shown rapid growth and ecosystem function comparable to natural forests within a decade or two. These restoration efforts are labor-intensive and expensive, but they show that we can actively help ecosystems recover. We're not just passive observers of decline, we can be active participants in recovery. Fisheries management has also shown that fish populations can recover when properly managed. Several fish stocks that were severely depleted have rebuilt after catch limits were implemented and enforced. Atlantic striped bass were overfished to the brink of collapse in the 1980s. Strict regulations were implemented, including a complete moratorium on fishing in some areas. The population recovered, and striped bass are now abundant along the east coast. Pacific halibut were severely overfished in the early 20th century. International cooperation between the US and Canada led to management measures that allowed the population to recover. The halibut fishery is now one of the best managed in the world. These success stories share common elements: strong regulations based on scientific assessment, effective enforcement, and patience. Recovery doesn't happen overnight. It takes years or decades for fish populations to rebuild. But the examples prove that recovery is possible. The ocean is resilient when given the opportunity to heal. Now let's talk about the deep ocean in ways we haven't fully explored yet. The deep ocean is the largest habitat on Earth by volume, yet it remains almost entirely unexplored. We've sent 12 people to the moon, but only 3 people have been to the deepest point in the ocean. The deep ocean is not empty or boring, as was once thought. It's full of life, from the microbes in sediments to fish swimming in the water column, and it plays crucial roles in regulating Earth's climate and chemistry. The deep ocean stores enormous amounts of carbon that sinks from the surface, either as organic matter or as calcium carbonate shells, can remain in the deep ocean for hundreds or thousands of years. This deep ocean carbon storage is crucial for regulating atmospheric carbon dioxide. If the biological pump weakens, if less carbon sinks to the deep ocean, more will remain in the atmosphere, accelerating climate change. There's concern that warming and changing ocean circulation could reduce the efficiency of the biological pump. The deep ocean also stores heat. It takes centuries or millennia for surface water to mix with the deep ocean, so heat absorbed at the surface now will continue affecting ocean temperatures for centuries. This thermal inertia means that even if we stopped all greenhouse gas emissions today, the ocean would continue warming for decades or centuries. Deep sea mining is an emerging threat to the deep ocean. Companies want to extract mineral nodules from the abyssal plain and to mine hydrothermal vents for metals. These activities would destroy seafloor habitats that took millions of years to develop. The organisms that live in the deep ocean are slow-growing and long-lived. Recovery from disturbance would take decades, centuries, or might not happen at all. Many deep-sea species have small populations and limited ranges. Mining could drive species extinct before we even know they exist. There's intense debate about whether deep-sea mining should be allowed. Proponents argue that it's less environmentally damaging than land-based mining. Opponents argue that we shouldn't destroy deep-sea ecosystems to extract metals when we could reduce consumption and recycle more effectively. The International Seabed Authority regulates mining in international waters, but regulations are still being developed. Several countries have obtained exploration licenses, and commercial mining could begin within a few years. Once mining starts, it will be difficult to stop. Economic interests will argue for expansion, and the deep ocean, out of sight and largely unknown, will continue to be treated as a sacrifice zone. The deep ocean deserves protection, not just because it might contain species useful to humans, though it probably does, but because it's a vast, ancient, and irreplaceable part of our planet. It has value in its own right, independent of human uses. We need to decide, as a global society, what kind of relationship we want with the deep ocean. Do we want to exploit it, extracting resources until nothing remains? Or do we want to protect it, preserving these ancient ecosystems for future generations? These are not easy questions, and they don't have simple answers. But they're questions we need to address now, before irreversible damage is done. The ocean is calling us to make a choice. Will we continue treating it as an infinite resource to exploit, or will we finally recognize it as a finite, fragile, and precious part of our planet that needs protection? The answer will determine the ocean's future, and since the ocean's future is inseparable from our own, it will determine our future too. As you rest now, let these thoughts settle in your mind like sediment drifting to the ocean floor. Think about the interconnections, how every part of the ocean affects every other part, and how the ocean affects everything on land. Think about the choices we face, the urgency of the problems, and the possibility of solutions. Think about the ocean not as a distant place, but as part of your own life, your own breath, your own existence. The ocean is not separate from you. You are made mostly of water, water that came from the ocean billions of years ago. You breathe oxygen produced by ocean phytoplankton. You live on a planet shaped and regulated by ocean processes. When the ocean thrives, you thrive. When the ocean suffers, you suffer. This is not metaphor or poetic language. It's literal truth. So as you drift into sleep, carry with you a sense of connection to the vast blue world that covers our planet. Carry with you a sense of responsibility for protecting it. And carry with you a sense of hope, because the ocean is showing us that recovery is possible when we make the effort. The mysteries of the ocean will continue to unfold for as long as humans exist to explore them. Every generation will make new discoveries, answer old questions, and encounter new mysteries. Your generation, the people alive today, will determine whether those future discoveries happen in a healthy ocean or a degraded one, whether future explorers find abundance and diversity or emptiness and loss. Wake ready to be part of the solution. The ocean's story continues, and you are part of it. But let's talk about what being part of the solution actually means, because it's easy to feel overwhelmed by the scale of ocean problems. Climate change, overfishing, pollution, acidification, these are planetary scale issues that no single person can solve alone. Yet every major change in history started with individuals making different choices. The ocean needs us to think differently about our relationship with it. For most of human history, we've treated the ocean as separate from ourselves, as something out there that we can use without consequence. We've thrown our waste into it, harvested its creatures without restraint, and assumed it would always remain the same. That assumption was always wrong, but the consequences of our actions were slow to manifest. Now they're manifesting rapidly, and we can no longer pretend the ocean is infinite or unchangeable. Every action we take has consequences that ripple through ocean systems, and understanding those connections is the first step toward making better choices. Let's talk about the ocean's food webs in much greater detail, because they're more complex and more fragile than most people realize. Food webs are not simple linear chains where small fish eat plankton, medium fish eat small fish, and large fish eat medium fish. They're intricate networks with multiple connections and feedback loops. In the open ocean, the food web starts with phytoplankton, microscopic organisms that photosynthesize. But there are thousands of phytoplankton species, each with different characteristics, different nutritional values, different growth rates. The composition of phytoplankton communities affects everything else in the food web. Zooplankton graze on phytoplankton, but different zooplankton species prefer different phytoplankton. Some zooplankton are generalists, eating whatever's available. Others are specialists, feeding on specific phytoplankton types. If the phytoplankton community changes, the zooplankton community changes in response. Small fish like anchovies and sardines feed on zooplankton. These small fish are incredibly important because they're the link between microscopic plankton and larger predators. They convert the energy stored in tiny plankton into packages that larger animals can eat. But small fish populations fluctuate wildly, sometimes changing by factors of 10 or more within a few years. These fluctuations are driven by ocean conditions, predation, and fishing pressure. When small fish populations crash, everything that eats them suffers. Seabirds that specialize in eating small fish can experience mass die-offs when their prey disappears. Along the California coast, seabird populations have declined dramatically as anchovy and sardine populations have fluctuated. Some species that once numbered in the millions now number in the thousands. Marine mammals also depend on small fish. Humpback whales, which feed on krill and small fish, have changed their migration patterns as prey distributions shift. Sea lions and fur seals that once thrived on abundant fish now struggle to find enough food. And it's not just natural predators that depend on these fish. Commercial fisheries harvest enormous quantities of small fish, mostly to make fish meal for aquaculture and livestock feed. This creates direct competition between wildlife and human industries. The complexity of food webs means that fishing affects not just the target species, but everything connected to it. When we remove predators like tuna and sharks, prey populations can explode, then crash when they exceed the carrying capacity. When we remove prey like sardines, predators starve, and the effects cascade through the system in unexpected ways. Removing large predators can lead to an increase in medium-sized predators, which then overconsume their prey, leading to collapse of the entire system. This has happened in several marine ecosystems, creating what ecologists call trophic cascades. In the North Atlantic, overfishing of cod led to an explosion of sea urchin populations. The urchins overgrazed kelp forests, creating urchin barrens, underwater deserts where once thriving kelp forests stood. The loss of kelp affected hundreds of species that depended on kelp forest habitat. Restoring the ecosystem required not just stopping cod fishing, but also actively removing urchins to allow kelp to regrow. It's been a slow process, and some areas still haven't recovered decades later. These examples show that we can't manage species in isolation. The ocean is an interconnected system, and our actions reverberate through it in complex ways. Let's talk about something we haven't fully explored, the ocean's twilight zone, in much greater detail. The mesopelagic zone, from 200 to 1,000 meters depth, is one of the ocean's largest habitats by volume, and it's full of life, far more than scientists suspected until recently. The biomass in the twilight zone is estimated at several billion tons, possibly more than all fish in surface waters combined. Most of this biomass consists of small fish, squid, and crustaceans. These organisms have adapted to life in dim light, where shadows can mean death. Many twilight zone organisms are nearly transparent, making them difficult to see. Others are silvery, reflecting what little light exists to blend with the background, and most have large eyes to capture every available photon. But the most remarkable thing about the twilight zone is the daily vertical migration we've mentioned. Every evening, billions of organisms rise from the twilight zone toward the surface to feed. They spend the night in productive surface waters, consuming phytoplankton and zooplankton. Then, before dawn, they descend back to the safety of the twilight zone. This migration is visible on sonar as a dense layer that rises and falls with the sun. Early sonar operators thought they were seeing the sea floor, but the floor moved, rising at dusk and descending at dawn. Eventually, they realized they were seeing a biological layer, the deep scattering layer formed by countless organisms. The migration serves an important purpose. By feeding at the surface and then descending to digest, these organisms transport carbon from the surface to the deep ocean. This biological carbon pump is one of the ocean's most important functions. It keeps carbon dioxide out of the atmosphere by moving organic carbon to depths where it's sequestered for centuries. Without this vertical migration, atmospheric carbon dioxide would be significantly higher. But the twilight zone is now being targeted for fishing. As surface fish stocks decline, fishing companies are looking deeper. The technology exists to catch twilight zone fish on an industrial scale, and there's a push to develop fisheries for these previously unexploited stocks. The problem is we don't understand the twilight zone ecosystem well enough to know what would happen if we started removing billions of tons of fish. These fish are food for everything above them: tuna, swordfish, dolphins, whales. They play a crucial role in carbon cycling, and their biology, lifespans, reproduction rates, and population dynamics are poorly understood. Removing large quantities of twilight zone fish could collapse predator populations. It could reduce carbon sequestration, accelerating climate change. It could destabilize the entire food web in ways we can't predict. Some scientists are calling for a moratorium on twilight zone fishing until we understand the ecosystem better. They argue that we should learn from past mistakes when we overfished species without understanding their role in the ecosystem. Others argue that we need new protein sources for a growing human population, and the twilight zone represents a massive untapped resource. They believe we can fish sustainably if we're careful and monitor populations. This debate is happening now, and decisions will be made in the next few years. The twilight zone represents one of the last major unexploited ecosystems on Earth. What we decide to do with it will reveal whether we've learned anything from past mistakes. Let's talk about ocean noise pollution in greater depth, because this is an underappreciated threat. The ocean is not naturally quiet. It's full of biological sounds: waves, rain, ice, and geological activity. But human-generated noise has increased dramatically over the past century. Shipping is the primary source of ocean noise. Propellers cavitate, creating bubbles that collapse and produce noise. Engines vibrate, creating low-frequency hums that propagate for miles. There are tens of thousands of ships at sea at any given time, creating a constant background rumble. This noise has increased by 10 to 100 times in many areas since the 1960s. In some busy shipping lanes, noise levels have doubled every decade. The cumulative effect is that the ocean is much louder than it was when most marine mammals evolved. Marine mammals rely on sound for communication, navigation, and finding food. Whales can communicate across hundreds or thousands of miles in quiet water. But in noisy water, their communication range shrinks dramatically. Imagine trying to have a conversation at a rock concert. You can still talk, but the other person can hear you only if they're very close. That's what marine mammals experience in the modern ocean. The noise doesn't just interfere with communication, it also causes stress, elevated stress hormones, and physiological damage. Very loud noises, like military sonar or seismic surveys, can damage hearing or even cause death. There have been documented cases of mass strandings following naval exercises. Whales beach themselves with damaged ear structures, hemorrhaging in the tissues around their ears. The correlation between sonar exercises and strandings is strong enough that some countries have restricted sonar use in sensitive areas. Seismic surveys for oil and gas exploration create some of the loudest sounds in the ocean. Air guns fire repeatedly, creating pulses of sound that penetrate the seafloor to map geological structures. These surveys can last for weeks or months, subjecting marine life to continuous loud noise. Studies have shown that seismic surveys affect fish behavior, reduce catch rates in nearby fisheries, and may damage fish eggs and larvae. The effects on marine mammals are harder to quantify, but are probably significant. Construction activities also create intense underwater noise. Pile driving for offshore wind farms, bridges, and other structures produces impacts that propagate through water. These sounds can injure or kill fish, and disturb marine mammals over large areas. Mitigation measures can reduce but not eliminate these impacts. Ships can slow down, which reduces propeller noise and also reduces whale strikes. Acoustic barriers can be used during construction to reduce noise propagation. Seismic surveys can be timed to avoid sensitive periods when whales are present. But the fundamental issue is that we've made the ocean much noisier, and marine life is suffering as a result. Reducing ocean noise should be a priority, but it receives far less attention than other forms of pollution. Let's talk about something hopeful: traditional ecological knowledge and ocean conservation. Indigenous communities have been living with and learning from the ocean for thousands of years. They've developed sophisticated understandings of ocean ecosystems, fish behavior, and sustainable harvesting practices. Pacific Island communities, for example, have traditional management systems that protected reef areas and regulated fishing. Certain reefs were closed to fishing during spawning seasons. Others were protected permanently as nursery areas. These practices were based on centuries of observation and experience. When colonial powers arrived, many of these traditional systems were dismantled. Open access fishing replaced traditional management, and reef health declined. Now many communities are reviving traditional practices, combining them with modern science. The results have been positive. Community-managed marine areas in the Pacific have shown rapid recovery of fish populations and reef health. The combination of local knowledge and scientific monitoring creates effective management. Indigenous communities in the Arctic have detailed knowledge of sea ice, marine mammal behavior, and ecosystem changes. This knowledge complements scientific data and provides insights that scientists might miss. For example, Inuit hunters noticed changes in ice conditions and seal behavior years before scientists documented them. Their observations helped researchers understand how rapidly the Arctic is changing. Traditional knowledge is not a replacement for science, but it's a valuable complement. It provides long-term perspective, local detail, and practical wisdom that scientific studies might lack. And indigenous communities often have conservation ethics that prioritize long-term sustainability over short-term gain. They understand that their children and grandchildren will depend on the same resources, so they manage accordingly. Many marine protected areas are now being established in collaboration with indigenous communities. These co-managed areas respect traditional rights and knowledge while applying modern conservation techniques. The results show that conservation is most successful when local communities are involved and benefit from protection. Let's talk about coral reefs in even greater depth, because they're one of the ocean's most important and most threatened ecosystems. Coral reefs cover less than 1% of the ocean floor, but support about 25% of all marine species. This extraordinary biodiversity makes reefs crucial for ocean health. Reefs provide habitat structure that creates niches for countless species. The complex three-dimensional architecture of a healthy reef offers hiding places, feeding areas, and breeding sites. Fish, invertebrates, algae, and microorganisms all find homes in the reef. Many commercially important fish species depend on reefs for at least part of their life cycle. Juveniles use reefs as nursery areas, hiding from predators until they're large enough to venture into open water. Reefs also protect coastlines from erosion and storm damage. The reef structure breaks waves, reducing their energy before they reach shore. During storms, reefs absorb wave energy that would otherwise damage coastal communities. And reefs are sources of food for millions of people. Small-scale fishers in tropical countries depend on reef fish for protein and income. The fish caught on reefs feed communities across the tropics. But reefs are dying at an alarming rate. We've discussed bleaching, but reefs face multiple stresses. Overfishing removes key species, disrupting reef ecology. Pollution from land, particularly excess nutrients, fuels algae growth that smothers corals. Physical damage from anchors, groundings, and destructive fishing practices destroys reef structure. And climate change is the overarching threat. Warming water causes bleaching. Acidification makes it harder for corals to build skeletons. Stronger storms physically damage reefs. The combination of stresses is overwhelming reef resilience. Healthy reefs can recover from bleaching if conditions return to normal. But when reefs face multiple stresses simultaneously, recovery becomes difficult or impossible. Many reefs are caught in degradation spirals. Stressed corals are vulnerable to disease. Dead corals are colonized by algae. Algae overgrowth prevents new coral larvae from settling. The reef shifts from coral-dominated to algae-dominated, and the shift is often permanent. Some scientists estimate that 70 to 90% of coral reefs could be gone by 2050 if current trends continue. This would be catastrophic for ocean biodiversity and for the human communities that depend on reefs. But there's still hope. Some reefs are more resilient than others. Reefs in areas with naturally variable temperatures seem better able to tolerate heat stress. Reefs with high genetic diversity recover faster from bleaching. And reefs that are protected from local stresses like overfishing and pollution can better withstand climate impacts. Scientists are working on multiple approaches to help reefs survive. Selective breeding programs are identifying heat-tolerant coral strains. Assisted evolution techniques are speeding up coral adaptation. Coral nurseries are growing corals that can be transplanted to degraded reefs. Some researchers are even exploring radical interventions like shading reefs to reduce heat stress or adding alkaline materials to counteract acidification. These approaches are controversial and might not work at scale, but they show how desperate the situation has become. The best hope for reefs is rapid reduction in greenhouse gas emissions. Without that, no amount of local management or intervention will be enough. But local actions still matter. Protecting reefs from overfishing, reducing pollution, and establishing marine protected areas all increase reef resilience. These actions buy time, giving reefs a better chance to adapt to changing conditions, and they preserve genetic diversity, the raw material for evolution. The more diverse coral populations are, the more likely some individuals will have traits that allow survival in warmer, more acidic water. Coral reefs have survived past climate changes and mass extinctions. They're resilient over geological timescales, but the current rate of change is unprecedented and reefs are struggling to keep up. Whether they survive depends on what we do in the next few years. Let's talk about ocean plastics in even more detail, because this problem is more complex than it first appears. When we think of ocean plastic, we often imagine floating garbage patches or sea turtles with plastic bags. But most ocean plastic is invisible to the naked eye. Microplastics, particles smaller than 5 millimeters, are everywhere in the ocean. They come from the breakdown of larger plastic items, but also from synthetic clothing fibers, tire dust, and plastic pellets used in manufacturing. Every time you wash synthetic clothing, thousands of microfibers are released. These fibers pass through wastewater treatment plants and into rivers and eventually the ocean. One study estimated that a single load of laundry can release over 700,000 microfibers. Tire dust is another major source. As tires wear down on roads, tiny particles of synthetic rubber are released. Rain washes these particles into storm drains and waterways. Some estimates suggest tire dust might be one of the largest sources of microplastics entering the ocean. Once in the ocean, microplastics are ingested by organisms at every level of the food web. Plankton consume them, mistaking them for food. Small fish eat the plankton, ingesting the plastic along with them. Larger fish eat the small fish, accumulating more plastic. This bioaccumulation means that predators at the top of the food web, including humans, are exposed to concentrated doses of plastic. But microplastics aren't just inert particles. They absorb toxic chemicals from the water, persistent organic pollutants, heavy metals, and other contaminants concentrate on plastic surfaces. When organisms ingest the plastic, they're also exposed to these concentrated toxins. The health effects of microplastic ingestion are still being studied. Laboratory experiments have shown that microplastics can cause inflammation, disrupt hormone systems, and damage tissues. But translating these findings to real-world impacts on wild populations is difficult. What we do know is that plastic is ubiquitous. It's been found in fish from the deepest ocean trenches. It's in Arctic ice and Antarctic snow. It's in seafood that humans consume. We're all exposed to microplastics, though the health implications remain uncertain. Nanoplastics, particles even smaller than microplastics, are an emerging concern. These particles are so small they can cross cell membranes and potentially accumulate in tissues. Some research suggests nanoplastics might be able to cross the blood-brain barrier. The detection and measurement of nanoplastics is challenging because they're so small, but preliminary studies suggest they might be even more widespread than microplastics. Addressing plastic pollution requires action at every level. At the source, we need to reduce plastic production and use single-use plastics are particularly problematic because they're used briefly, then discarded. Better waste management is crucial. Much plastic enters the ocean from improper disposal, particularly in countries with inadequate waste infrastructure. Improving collection and recycling systems would reduce ocean plastic inputs. But recycling isn't a complete solution. Many plastics can't be recycled economically, and recycling itself releases microplastics into the environment. The most effective approach is to reduce plastic use overall. This requires systemic changes in how products are packaged and delivered. It requires businesses to adopt alternative materials and circular economy models. And it requires consumers to choose products with less packaging. Some progress is being made. Many jurisdictions have banned single-use plastic bags. Some companies are experimenting with plastic-free packaging. Bottle deposit systems increase recycling rates. But plastic production is still increasing globally. The petrochemical industry views plastic as a growth market as fossil fuel use for energy declines. Without stronger regulations and incentives, plastic pollution will continue to worsen. The ocean can't solve this problem on its own. Plastic doesn't biodegrade in any meaningful time frame. The plastic entering the ocean today will be there for centuries or millennia. We're creating a permanent legacy of pollution that future generations will inherit. Let's talk about something we haven't fully explored: ocean methane and its implications for climate. Methane is a powerful greenhouse gas, roughly 25 times more potent than carbon dioxide over a century timescale. The ocean contains enormous amounts of methane in various forms. Methane hydrates, which we've mentioned, are ice-like structures where methane is trapped in frozen water. They exist in seafloor sediments and Arctic permafrost, forming under specific conditions of cold temperature and high pressure. The amount of methane in hydrates is staggering, possibly exceeding all other fossil fuel reserves combined. But most of this methane is stable under current conditions. The concern is that warming could destabilize hydrates, releasing methane into the atmosphere. If ocean temperatures rise, or if sea level drops, hydrates could decompose. The methane would bubble up through the water column and potentially reach the atmosphere. This would create a positive feedback loop. Warming causes methane release. Methane causes more warming, which causes more methane release. This is the methane clathrate gun hypothesis, and it's controversial. Some scientists think it's a real risk, potentially catastrophic. Others think the risk is overstated, that methane released underwater is mostly oxidized before reaching the atmosphere. The truth is we don't have enough data to be certain. Methane releases have occurred in Earth's past, associated with rapid warming events. The Paleocene-Eocene thermal maximum, 56 million years ago, saw rapid warming of 5-8 degrees Celsius. Some evidence suggests massive methane releases contributed to this event. More recently, scientists have detected methane plumes in Arctic waters where permafrost is thawing. These releases are currently small, but they could increase as warming continues. The East Siberian Arctic shelf is a particular concern. This shallow sea contains large amounts of methane in both hydrates and free gas trapped under permafrost. As permafrost thaws, the cap keeping methane trapped could fail, releasing massive amounts. Monitoring methane in the ocean is challenging. The ocean is vast, and methane release can be localized and episodic. But research efforts are increasing, with more instruments deployed to measure methane concentrations. Natural methane seeps exist throughout the ocean, places where methane bubbles up from the seafloor. These seeps support unique ecosystems, with bacteria that oxidize methane and organisms that feed on the bacteria. Human activities also release methane into the ocean. Oil and gas extraction can cause methane leaks. Damaged offshore infrastructure releases methane, and the ocean absorbs some methane from the atmosphere. The ocean's role in the methane cycle is complex and not fully understood, but it's clear that ocean warming could trigger methane releases that accelerate climate change. This is another feedback loop we need to monitor carefully. Let's talk about something that offers perspective: the ocean's timescales. We often think in terms of human lifespans, decades at most, but the ocean operates on vastly longer timescales. The water in the deep ocean can be over 1,000 years old. It sank in the North Atlantic when medieval Europeans were building cathedrals. It's been circulating through the ocean depths ever since, finally rising again in the Pacific or Indian Ocean. This means that changes we make today won't fully manifest for centuries. We're altering the chemistry and temperature of water that won't resurface until our great-great-great-grandchildren are gone. Ocean sediments accumulate slowly, typically less than an inch per 1,000 years in the deep ocean. The sediment cores that scientists drill represent millions of years of history compressed into hundreds of feet. Coral colonies can live for centuries. Some deep-sea corals are thousands of years old, living in cold, dark waters where growth is incredibly slow. These corals were already ancient when human civilization began. Marine organisms have evolved over billions of years. The basic body plans of major animal groups were established over 500 million years ago. Evolution works on these vast timescales, testing variations across millions of generations. The changes we're imposing on the ocean are happening in decades, faster than most species can adapt. We're compressing thousands or millions of years of change into single human lifetimes. This mismatch of timescales is why ocean ecosystems are struggling. Evolution can't keep pace with the rate of change. Species adapted to specific conditions find those conditions shifting faster than they can adapt. Some species might adapt through genetic changes or behavioral flexibility, but many will go extinct, unable to adjust quickly enough. The ocean will eventually reach a new equilibrium. Even if we disappeared tomorrow, the ocean would continue changing for centuries as it adjusts to the heat and carbon we've added. Eventually, over thousands or millions of years, the ocean would recover. Carbon would be locked back into rocks through weathering. Species would evolve to fill empty ecological niches. New ecosystems would develop, different from what existed before but functional in their own way. But this recovery would take longer than human civilization has existed, and it wouldn't restore what was lost. The specific species that go extinct are gone forever. Understanding these timescales provides perspective. The ocean is ancient and will persist long after humans are gone. But the ocean we know, the ocean that supported human civilization, is changing rapidly. We're not destroying the ocean. We can't. It's too vast and resilient. But we're changing it into something different, something less hospitable to the species that currently exist, including ourselves. Let's talk about ocean observation and monitoring, because understanding change requires measuring it. Oceanography has come a long way from ships collecting water samples and measuring temperature with thermometers. Today we have satellites measuring ocean color, temperature, and sea level from space. We have autonomous floats drifting with currents, diving to depth and surfacing to transmit data. We have underwater gliders that can operate for months, collecting continuous measurements. The Argo program has deployed thousands of floats across the global ocean. These floats drift at depth, surface every 10 days to transmit data, then dive again. They measure temperature, salinity, and sometimes oxygen and other properties. The data from Argo floats has revolutionized our understanding of ocean heat content and circulation. We now have continuous global coverage of the upper ocean. This data feeds into climate models and weather forecasts. Satellites provide a different perspective, measuring the ocean surface from above. Ocean color satellites detect phytoplankton concentrations by measuring how light reflects off the water. Different phytoplankton communities reflect light differently, allowing scientists to track plankton blooms and ecosystem changes. Sea surface temperature satellites measure heat with high precision. This data tracks marine heat waves, El Niño events, and long-term warming trends. Sea level satellites use radar to measure ocean height with millimeter precision. They've documented the accelerating rate of sea level rise and mapped regional variations. Ocean monitoring also happens from ships, though ship-based observations are declining as autonomous systems improve. Research vessels still conduct detailed surveys, collecting water samples, deploying instruments, and studying specific regions intensively. Submarines and submersibles allow direct observation of the deep ocean. Human-occupied submersibles carry scientists to places they couldn't otherwise reach. Remotely operated vehicles explore dangerous or long-duration missions. Underwater observatories are being established in various locations. These permanent installations on the seafloor continuously measure conditions and observe ecosystems. Some are cabled to shore, providing real-time data and power. Others use batteries and surface buoys to transmit data. Acoustic monitoring uses underwater microphones to listen to the ocean. These hydrophones detect whale vocalizations, earthquake sounds, ship noise, and other acoustic signals. Long-term monitoring reveals changes in animal behavior and population trends. Citizen science is also contributing to ocean monitoring. Recreational divers report observations of fish, corals, and water conditions. Fishing communities provide data on catches and observations. Smartphone apps allow anyone to report marine life sightings. All this monitoring generates enormous amounts of data. The challenge is processing and analyzing it to extract useful information. Artificial intelligence and machine learning are increasingly used to analyze ocean data, finding patterns that humans might miss. Despite all these observations, the ocean remains undersampled. Most measurements are concentrated in the northern hemisphere, particularly the North Atlantic and North Pacific. The Southern Ocean, the Indian Ocean, and the tropical regions have far fewer observations. The deep ocean is particularly poorly monitored. Most instruments measure the upper 2,000 meters. The water below that, representing most of the ocean's volume, is rarely sampled, and many important properties are difficult to measure. Ocean currents, mixing rates, biological productivity, and ecosystem interactions all require specialized instruments and intensive sampling. We're getting better at monitoring the ocean, but we still have huge gaps in our knowledge. Every new observing system reveals phenomena we didn't know existed. The ocean continues to surprise us, showing complexity beyond what we anticipated. As we approach the end of this extended journey through ocean mysteries, let's reflect on what we've learned. The ocean is vast, covering most of our planet. It's deep, extending miles below the surface in places. It's old, billions of years old, older than most of the continents. The ocean is full of life, from microscopic bacteria to the largest animals ever to exist. This life is diverse, adapted to every imaginable environment, from warm tropical reefs to cold polar seas to the crushing pressures of the deep trenches. The ocean is dynamic, constantly moving, mixing, changing. Currents circle the globe, waves ripple across the surface, tides rise and fall. Nothing in the ocean is static. The ocean is powerful, capable of generating hurricanes, tsunamis, and rogue waves. It shapes coastlines, influences climate, and sustains life on land. The ocean is mysterious, hiding secrets in its depths that we're only beginning to uncover. New species, new phenomena, new connections between ocean processes. Every expedition reveals something unexpected. The ocean is vulnerable, affected by human activities in ways we're only now beginning to understand. Warming, acidification, pollution, overfishing, all are changing the ocean. The ocean is resilient, capable of recovery when given the chance. Protected areas show rapid improvements. Fish populations rebound when properly managed. Ecosystems heal when stresses are removed. The ocean is essential, providing oxygen, food, climate regulation, and countless other services. Without a healthy ocean, human civilization cannot persist. The ocean is connected to the atmosphere, to the land, to every living thing. Changes in the ocean affect everything else, and the ocean is part of you. The water in your body came from the ocean. The oxygen you breathe was produced by ocean phytoplankton. Your existence depends on ocean processes. As you rest now in the quiet darkness, imagine yourself floating on the ocean's surface. Above you, stars wheel across the sky. Below you, miles of water stretch down into darkness. Around you, the ocean breathes, swelling and subsiding with gentle rhythm. Beneath the surface, life goes on in all its complexity. Whales sing in the distance, their voices carrying through the water. Fish school in the twilight zone, preparing for their nightly migration. In the deep, strange creatures hunt in eternal darkness. On the ocean floor, Hydrothermal vents spew mineral-rich water, supporting impossible ecosystems. Sediments accumulate slowly, recording history in layers. Tectonic plates shift and grind, reshaping the planet. The ocean continues its ancient rhythms, largely indifferent to human concerns. It will be here long after we're gone, adjusting to whatever changes we've made, evolving new forms of life, continuing the story that began billions of years ago. But right now, in this moment, the ocean and humanity are intertwined. Our fates are linked, our futures inseparable. What happens to the ocean happens to us. What we do to the ocean, we do to ourselves. This is not metaphor, it's reality. The ocean is calling us to change, to make different choices, to live in ways that honor the connection between us and the blue world that covers our planet. Will we answer that call? Will we find the wisdom and courage to protect what sustains us? The answer is being written now, in the choices we make each day. Sleep well, dreaming of deep water and distant currents. Wake with the knowledge that you are part of something vast and ancient. Wake ready to honor that connection. The ocean's story continues. Your part in it is just beginning. Good night. May the ocean's rhythm soothe you into rest. May its mysteries inspire your dreams. And may its wisdom guide your waking hours. The tide goes out. The tide comes in. The ocean endures. And so must we, together with it, protecting what gives us life, cherishing what makes our planet unique in the known universe. The ocean, our origin, our sustenance, our future. Sleep now. The ocean watches over us all. Good night.